Tranquilo? Posso falar? Bom dia a todos. Antes de mais nada, a gente gostaria de pedir desculpas. Tivemos alguns problemas aqui com relação à transmissão. Ontem nós tivemos vários problemas de transmissão e tivemos pouco tempo para resolver esses problemas. De modo que agora parece que está tudo ok. E eu vou começar com uma mensagem do Noevaldo, que é a seguinte. Tivemos um dia difícil, mas estimulante. Ele está se referindo a ontem. Conhecemos agora com clareza nossas limitações e assim podemos agir. Sabemos que todos os esforços foram exercitados, mas a qualidade da transmissão foi insatisfatória. Por outro lado, tivemos a certeza de que os cursos online são viáveis e, quando transmitidos adequadamente, constituirá no principal mecanismo de aprimoramento técnico no Serviço Geológico do Brasil, CPRM. Espero que vocês não percam o entusiasmo, não desistiremos de viabilizar esse programa de capacitação. Assim, a diretoria autorizou a implementação de um mecanismo alternativo de transmissão. O mesmo visa garantir a qualidade e a viabilização do treino online. Hoje já implementamos uma nova transmissão com continuidade e qualidade visual. Ontem foi apenas o primeiro dia dessa caminhada que tenho certeza marcará a carreira profissional de todos vocês. Muito obrigado, Noevaldo Teixeira. Então, dito isso, a gente começa com a Lecture 5 do professor Charad, ok?
Okay, good morning. Bon dia. And sorry for the delay in starting this morning for technical reasons. Today I want to discuss Archean metallurgy. We looked at the evolution of the Archean yesterday, greenstone belts and so on. So today we want to look at the metallogenic deposits, and we're going to start with looking at greenstone belt hosted mesothermal lode gold deposits. So the Archean eon that we're going to discuss, from 4 billion to 2.5 billion years, is certainly a very important epoch in Earth's history, because there is a vast amount of mineral deposits, gold, copper, zinc, iron, nickel, that's found in the Archean. And it's a very important era for gold mineralization. Roughly 60% of the world's cumulative gold production has come out of Archean rocks. And of that, maybe about 20% comes from mesothermal lode gold deposits in greenstone belts. That's what we're going to talk about now in this lecture. And about 40% has come out of the paleoplacer deposits of the Witwatersrand Basin in South Africa, which will be the subject of the next lecture. So if we just look schematically at the amount of gold that has come out from different geological units, you see that it's very, very unevenly distributed. There's a huge peak here in the Archean, because it's dominated by the Witwatersrand, which is the world's biggest individual gold field, and then the Archean greenstone belts, which provide a lot of gold in the Archean. And then there's really not that much gold throughout the Proterozoic, and then you see that there is another peak in the very young deposits associated with epithermal and porphyry-type mineralization in Cenozoic volcanic arcs. So it's a very kind of a bimodal distribution for gold deposits with geological time. So certainly the Archean is a time period when there is a lot of gold mineralization, and the Witwatersrand being it's controversial, but I will discuss it tomorrow in the next lecture rather, that it's a detrital gold. Then the question then is, where does that detrital gold come from? And the obvious source would be things like Archean greenstone belts. So we've looked at greenstone belts yesterday. They are deformed volcanic and sedimentary rocks, and some of the oldest sort of supracrustal volcano-sedimentary rock sequences in this age range from 3.5 to 2.5 billion years, Paleo to Neo-Archean in age. And they're called greenstones because of all the presence of green minerals, such as fuchsite and chlorite, actinolite, serpentine, which are all minerals that are formed under greenschist facies metamorphic conditions from precursor minerals like pyroxenes and olivine and things like that. So, and also epidote from alteration of calcic feldspars. So the characteristic green color of all these metamorphic minerals is what gives rise to the term greenstone, and that is what is applied to basically metamorphosed rocks under greenschist facies, mainly metavolcanic rocks. Now, I showed yesterday some early ideas about the stratigraphy in places like the Barberton Greenstone Belt, where you saw a lower ultramafic to mafic sequence in the Onverwacht group. In the upper part of the Onverwacht, there were more evolved rocks, rhyolites and dacites and so on, and possibly associated with intrusive granitoids intruding through the ultramafic sequence, and then overlain by the sedimentary Fictory and Moody's groups, predominantly argillaceous and arenaceous rocks, perhaps associated with volcanic arc and continental margin sort of environments. And just to summarize the greenschist facies, it's sort of, you're looking at temperatures between about 350 to 500 degrees centigrade, with pressures between 2 to about 8 or 10 maximum kilobars. And yeah, I'm not going to go into details about this. You all know a number of greenstone belts worldwide. In the Archean, there's examples here in Brazil, the famous ones in Australia, the Yilgarn, Pilbara, and the Canadian examples as well. There are also lesser known ones in India and South African ones, obviously, and Zimbabwe, which I talked about yesterday. So if we come to South Africa, there's a number of greenstone belts in South Africa. In the Kaapvaart Craton, I talked yesterday about the Barberton Greenstone Belt, but there are several others as well. They are not that well exposed. They're not as well known as the Barberton. So here's a sketch map of the Barberton of the Kaapvaart Craton, which shows you the Barberton Greenstone Belt, which is the largest of the South African greenstones. There are others, Murchison, Sutherland, Pietersburg, even Johannesburg. There is a greenstone belt just in the northern part of Johannesburg, and there's also in the western part of the Kaapvaart Craton the Amalia Madibe greenstone belts. So, in fact, many of the other greenstone belts also have got gold mineralization in them. And if you think about the Zimbabwe Craton I talked about yesterday, it's got more than 23 greenstone belts. All of them have got gold mineralization. So gold seems to be very, very common in most greenstone belt terrains everywhere around the world, and accounts for 20% of all gold that is mined. So, yeah, these are just some of the famous ones that I've mentioned. So in Brazil, you have your Morovelho, Raposo. Australia, these are just some of the famous mines. Mount Morgan, the Golden Mile in Kalgoorlie, the Kolar Goldfields in India, very famous gold producer. A number of deposits that are known in Zimbabwe. And in South Africa, the mines that are most famous are the ones around Barberton, the Fairview Sheba mines, which have been going for more than 100 years. But there are also deposits in some of the smaller greenstone belts as well. Also some recently opened gold mines there. In Canada, of course, you've got the famous Abitibi greenstone belt with all its famous gold deposits at Val d'Or and Timmins. Okay, so what we're going to talk about in these greenstone belts are these mesothermal load gold vein deposits, which occur mainly as sort of quartz plus or minus carbonate and sulfide bearing gold veins in a well-defined zone of mineralization, and they almost invariably are controlled structurally by faults or fissures in shear zones within the country rock. The thicknesses can vary from a few centimeters to more than 5 meters. In fact, some of the veins that I've seen in Kalgoorlie, for example, are just 1 millimeter thick, but it's 1 millimeter of pure gold. You can actually get very high grades in something like that. They are usually tabular and inclined or discordant to the sort of layering. So typically these are narrow zones compared to the length and the depth. They can extend for several hundreds of meters and extend to depths of perhaps more than a kilometer with little change in mineralogy or grade. So they're usually structurally controlled, and when you look at the host rocks that host these types of deposits, you find that if you just look at it in terms of volume, the mafic rocks that are found in the greenstone belts, the mafic tend to be the ones that are the most common host rocks for gold deposits. But most other rock types that are found in greenstone belts can also host gold. In ultramafic rocks, in grey-wacky shale sedimentary rocks, very important in the Barberton greenstone belt, where some of the most important deposits are actually hosted by the metasedimentary rocks rather than by the volcanic rocks. Whereas if you look at the Zimbabwean greenstone belts, most of the gold mineralization is either in mafic volcanic rocks or with banded iron formations. So banded iron formations are also very important. And one of the things that's in common with all of these different host rocks for the gold mineralization is, firstly, its structure. It's important. The most important thing to get the fluids into the rocks in the first place. And secondly, is the presence of iron, because I will show you the reactions that are very important for precipitating gold out of gold-bearing hydrothermal solutions. You need to have iron in your host rocks, and that's one of the important controls. One of the common things associated with this type of gold deposits is hydrothermal alteration. It's because these fluids are formed by hot hydrothermal fluids which are reacting with the country rocks, and so there's some kind of a chemical reaction going on that producing mineralogical changes in the wall rocks, usually carbonate, sericite, chlorite alteration, together with sulfides, pyrite, and so on. Often the hydrothermal alteration is a giveaway to mineralization because the envelope of alteration is much greater than the actual mineralization itself. So it's a key to zoom in on the mineralized zones. So the ore formation, you're looking at the hydrothermal fluids, temperatures of perhaps 200 to 350 degrees centigrade, and very shallow depths, so 1 to 3 kilobars pressures for the fluids. Here we see an example of carbonate alteration in a banded iron formation. This is from the Madibe gold mine in one of the smaller greenstone belts in South Africa. Here we see carbonate chlorite alteration in a banded, an altered banded iron formation from that same deposit. And here we see some brittle quartz sulfide veins that are cut by brittle faults that are carrying mineralization from that same deposit. Now, if we look at the mineral associations that are found in this type of deposit, you have usually a little bit of silver that is always present, so some amalgam that is associated with gold to silver ratios, maybe about 9 to 1, with considerable variation between the deposits. The gold grades are relatively high, in the range of, say, 5 to 30 grams per ton. Some of the very rich deposits are like an ounce to the ton. But of course, it depends on the gold price, what is economic to mine. In many cases, when the gold price was very high a few years ago, you could be mining sub 1 gram per ton deposits if they were close to surface and quite weathered. So the actual mining grades can be even lower than this, but you do get grades up to an ounce to the ton. It is very rare to find much higher grades than that. The ore minerals, generally pyrite, pyrrhotite, arsenopyrite, sometimes gold, silver tellurides, sometimes bismuth as well. There's many other associated minerals. It all depends on different deposits: galena, sphalerite, chalcopyrite, molybdenite, stibnite, scheelite, magnetite. These are all minor associated minerals that may be found in these deposits. The gangue minerals, usually alteration minerals and quartz, feldspar, carbonates, often sometimes tourmaline, sericite, chlorite, and in many cases also you may find a bit of chrome, muscovite, fuchsite, which is usually where the fluids have come through an ultramafic rock and have picked up chrome, and then you find this bright green mineral which is part of the alteration assemblage. So here we see some examples, the photomicrographs of the ore minerals. Gold inclusions are found in pyrite here, and then there's also other things like pyrrhotite. when you have ores like this, where the gold inclusions are found trapped within pyrite, it's called a refractory ore, because it's very difficult then to liberate the gold, and then you have to do something else to the ore before you can get the gold out. You have to roast or heat up the sulfides to release the gold, or you have to use a biogenic leach where the bacteria can attack the pyrites and liberate the gold or something like that. So this kind of gold deposit is not metallurgically very good. It's more expensive to treat, whereas if you've got free gold that is in quartz veins, it's much easier to treat that with normal sort of leaching processes. Anyway, let's look at the sort of the main models for the formation of these kinds of deposits. There are possibly two, there's a range of possibilities, but the two main models are usually the metamorphic model and the magmatic model. So in the metamorphic model, the actual origin of the ore-bearing fluids is from regional metamorphism, whether that's regional tectonic events, regional metamorphic events, which are dehydration reactions taking place, where you have early low-temperature hydrous minerals which are recrystallizing under metamorphic conditions to anhydrous minerals. They're giving off water during the process of metamorphic dehydration, and these hot hydrothermal fluids may dissolve and transport gold and other metals and to a place where it eventually gets transported. So basically in this metamorphic model you've got something happening in the lower crust, and this could be in fact partly related to granitic intrusions in the crust, which could be heating up the greenstone belts or interacting with fluids. And you need obviously structures that are going to channel these metamorphic fluids to upper crustal levels where they interact with the greenstone belts and produce the gold deposits. I'll come back to the actual interactions that take place, the chemical reactions that take place in the upper crust to trap the fluids. But the metamorphic model, the source of the fluids is regional metamorphism. And the evidence for that comes out of fluid inclusion studies, where the fluid inclusions might be dominated by things like CO2, which is one of the giveaways for metamorphism. The other model is the magmatic model, where the fluids may be related to late-stage magmatic or magmatic hydrothermal activity, where the actual source of the fluids is juvenile and coming from exsolving out of magmas. The fluids themselves are enriched in gold coming out of the magmas, and it is the magmas that are the source of the fluids, and the same sort of plumbing systems operate and transfer these magmatic hydrothermal fluids up into the upper crust, where they react with the greenstone belt lithologies to form gold deposits. So let's look at the kind of reactions that are important in trapping these kinds of gold deposits. So firstly, you need to transport gold, whether it's coming from a metamorphic source or a magmatic source. The fluids need to be able to pick up and transport gold. So we need to look at gold hydrothermal geochemistry for this. And if you look at the way gold is transported under reducing conditions, it would be transported as a bisulfide complex, gold HS2-. So gold plus H2S, this is forming under reducing conditions. You would get a bisulfide complex plus hydrogen. So this is the way in which most gold is actually soluble under hydrothermal conditions. It is not the only way you can dissolve gold, because if you have very oxidizing conditions, you can transport gold as a chloride complex. But for that you need very special conditions. You need extremely oxidizing conditions and extremely acidic conditions, which do not generally occur in the crust. It occurs under very special conditions, where you have very oxidized magmas, for example, or something like that. And you can transport gold under as chloride complexes under those conditions. But for the ones that we are talking about, most of the greenstone-hosted gold deposits, the gold is transported in a reduced form as a bisulfide complex, and by hot hydrothermal fluids, which are relatively reducing. And then you need to have a deposition mechanism to then destabilize the gold bisulfide complexes to deposit gold. So the depositional mechanism is usually to react the gold-bearing complexes with iron-rich minerals, because the reaction is very easy and very important. If you take the gold bisulfide complex and react with iron oxide, in whatever form it is, it could be in the form of magnetite or hematite, well, rarely hematite, but if it's FeO and it's found in a silicate mineral or in some oxide form, the gold bisulfide will react with that and will produce gold plus sulfide in this kind of a redox reaction. So the result of this will be to produce free gold plus sulfide. Sometimes the gold is trapped within the sulfide, like we have seen previously in the previous photograph, or the gold might be free, intergrown with the sulfide. Now, of course, this is just one reaction. There are many variations on this reaction depending on what else is in the fluid. If you have arsenic in the fluid, then you will produce arsenopyrite, not just pyrite. And if you've got bismuth or tellurium, then you may form bismuth tellurium bearing minerals as well. But this is an important reaction because it shows the importance of iron in your host rock as a chemical trap for these gold bearing bisulfide complexes. So they destabilize in the presence of iron. So whenever you've got a shear zone going through iron-rich rocks, whether they are basaltic rocks or banded iron formations or iron-rich greywackies or whatever, this is the type of reaction that's going to take place. Wall rock reaction is a very important mechanism for trapping these kinds of fluids. So let's look at just now some of the earliest gold mineralization that we know about in the world, which is in the oldest greenstone belt that's well preserved, the Barberton Greenstone Belt. And we find that, you know, we have a lot of mafic and ultramafic rocks in the Onverwacht group, but there are not many gold deposits in the Onverwacht group. There's a lot of secondary gold that is being panned from the southern part where the Onverwacht group outcrops, but there are really no major gold deposits that have been discovered yet in the Onverwacht group. When you look at the gold distribution within the Barberton Greenstone Belt, you see that a lot of gold is distributed around the northern part here, where you have a big pluton. This pluton is the Kaap Valley pluton, which is an intrusive granite, and you can see a huge concentration of big gold deposits around there. But if I just go back here, most of it is actually within the Fig Tree group, and maybe a little bit in the Moody's group, which are the sedimentary rocks in the upper part of the Barberton Greenstone Belt, and not so much within the Onverwacht and the other part of the Greenstone Belt. So structure certainly plays a very important part in localizing where the gold deposits are. And over here we see a major structure called the Eureka syncline, which is in juxtaposition to the Olundi syncline, which is another one. There are two synclines adjacent to each other, with the intervening anticline having been faulted out. So, the syncline itself has been refolded, so there are lots of brittle fractures associated with the refolding, and along the intersections of some of these fractures and the bedding planes is where you find the localization of some of the major gold deposits. So the Sheba gold mine here, the Fairview gold mine, they are found within this Eureka syncline, and there are other deposits in the northern part, the New Consort gold mine, which I will also mention as well. So here is the Fairview gold mine. It's a sort of a view of the ore chutes themselves, which generally tend to have a shape that is controlled by structure. So when you have a structure of a movement along a fault, and it opens up a space, and that is the plunge that you may find of different ore chutes that are occupied by mineralization. So here is a kind of a cross section through here, which shows some kind of a big shear zone, some interfolial folds, and along the movement along these structures is where you find the major ore shoots. But they are not planar, they are like isolated shoots that are controlled by dilational zones within the structures themselves. Here is a view of the Fairview gold mine, which is one of the biggest gold mines in the Barberton Greenstone Belt, and it is it sort of has one section of it which is the famous Sheba mine, and it is connected underground. The two sort of deposits are now one big deposit that's linked. Now the history of the Barberton Greenstone Belt started in the 1880s, in the early 1880s, when prospectors came out there and they discovered some extremely rich deposits. This is a remnant of one of those bonanza regions called the Golden Quarry. It was discovered by a man called Edwin Bray in 1885, and this is what remains of this particular deposit that was mined out. There's a shaft going up to the surface. So it just looks like a big cave. But in this little quarry, they found 50,000 ounces of gold from just 13,000 tons of ore. So it was running at an average grade of like 120 grams per ton. It was a rich bonanza. And this is the type of gold that came out of this particular area. So some of these, the Sheba mine is a spectacularly rich mine. For its entire history of more than 130 or 40 years, it's been running at an average of more than 1 ounce to the ton of gold, more than 30 grams per ton on average. So it's one of the most spectacular gold mines in the world. And the host rocks in this case are actually the Greywackies or the Fig Tree group, along which there are big shear zones. These are some photographs of the early days in the Barberton Greenstone Belt from the 1880s, when there were prospectors came from all parts of the world, from Australia, from California, and tried to make their fortunes. And yeah, there were lots of bars, and there's a remnant of a hotel that is still around today. You can see a lot of bottles of beer were drunk in those days. Okay, so that was the Sheba mine. And there are other deposits like the Lily mine in the Barberton Greenstone Belt. You can see lots of final folding, very tight shear zones within the Fig Tree shales. And when you look at a plan view of the mineralization, you can see big shear zones with these kinds of transfer structures, kind of a sigmoidal structure. If you look at it here, it's called a sigmoid curve along a fault, and the fault plane moves. You open up space along the fault plane, and that space is then mineralized with quartz veins. And that is the type of mineralization that you find here in Lily Gold Mine. Again, this is another one where you had a bonanza of very, very pockets of very rich gold that were found. This particular pocket yielded about 29 ounces. I think I've got another photograph of it later on. From the Lily Gold Mine, lots of rich visible gold. So these are the kinds of things that that all the prospectors read about, and which are bonanzas that are still coming out from these gold mines. There have been, well, the original studies on these gold deposits were done in the 60s and 70s, but there's still more modern studies continuing, including this one by Otto et al. This is a group from Aachen University in Germany, who've done modern studies on one of the oldest gold deposits in the world. This is at 3.2 billion years. This is the New Consort mine in the northern part of the Barberton Greenstone Belt. Again, the host rocks are the Fig Tree and the Moody's groups, mainly the Fig Tree group rocks, which are these ones here. And they've done a lot of work showing all the different alteration zones and looked at all the mineral assemblages. I'm not going to go into details about all of that. Just to show you that they've done, they've basically looked at the petrography of the gold, the mineralogy of the gold. The gold is associated with pyrite, pyrrhotite, as well as other minerals like lurlingite, which is iron arsenide, and sort of bismuth-bearing minerals and so on. So this is the the vein. This one has 60 ounces of gold from a pocket that was found in 1963, an extremely rich, perhaps a supergene enriched zone just about 30 meters below the surface. Very, very rich pocket with extremely rich gold. So 60 ounces today would be, multiply that by $1,200 an ounce. Okay, going to Zimbabwe now. If you look at the Zimbabwean greenstone belts, we have seen that they are much younger than the ones in Barberton. Barberton being about 3.2 billion years for the sedimentary rocks. The Zimbabwean greenstone belts are generally about 2.7 billion years. Most of them, there are some older ones, 2.9, but the bulk of the greenstone belts are between 2.8, 2.7 billion years, and they are intruded by this vast sea of late Archean 2.6 billion year potassic granitoids that stabilized the Zimbabwe craton. So Zimbabwe is a country where most of its gold mineralization comes out of Archean greenstone belts. And they've been mining gold in this country for more than 1,000 years. This was the whole basis of the great Zimbabwe civilization, which flourished in the 14th century. Gold is found everywhere, and today if you go to Zimbabwe, you always find small gold workings, one or two people with a little stamp mill going just the way it was going 100 years ago, and you can still find little operations like that all over the show, producing a few ounces of gold per month, but it's enough to keep a small worker going with his family and so on. And also, aside from the stamp mills, because they are actually mining solid veins, there are also a lot of artisanals who are doing mining in the rivers for alluvial gold. Now, in Zimbabwe, there is a famous deposit called Vubachikwe near the city of Bulawayo, south of Bulawayo. And this is in the Gwanda Greenstone Belt. And this is a deposit that I was involved in. I did a little discussion about it because there was a study that was done by several people who have written about this deposit. It's famous because a model was developed by Rod Fripp in the 1970s, which was a hydrothermal exhalative model, where he suggested that the gold that is hosted by iron formations is actually exhalative. It is formed during sedimentation, and that you are actually forming gold-bearing sulfide deposits due to some exhalative process on the sea floor. Now that model was, a number of people have believed that model back in the 70s and the 80s, and were applying it to other greenstone belts in the world. By contrast, there was a completely opposing model to that, which was the one by Phillips and Groves, which is a hydrothermal replacement model for Archean banded iron formation hosted gold deposits. And the Vubachikwe mine is in fact one of the classic areas where the hydrothermal model was developed originally by Rod Fripp, and there was another group by Zager and others who also published in Economic Geology a paper suggesting that this was an exhalative syngenetic type of deposit. So at the time when their paper was still in press, I managed to get hold of a reprint with a friend of mine. We visited this mine as underground, and what we saw is we were traveling through this ore deposit where the actual host is a sulfide facies iron formation. It's pyrrhotite, arsenopyrite with gold. And it's just continuous stratiform mineralization that you follow for hundreds of meters. But we followed this to the end of the workings underground, and this is what we saw. What you see in this image here is what we saw in the end of the face where they stopped mining. And what it was is an iron formation, but it is a magnetite facies iron formation. You can see a magnet here that is stuck to the wall. That's a hammer for scale. So we had been following a sulfide facies iron formation, but in the end, what you see is the same bed is a magnetite facies iron formation. And so I simply looked up and I saw the contact. And the contact is very interesting. Here it is in the roof. On this side, on the left-hand side, is magnetite. You can see a magnet stuck to the magnetite. And the same bed, you follow it along, and it is sulfide. So it is very, very clear. It's the same horizon. It's not a phase change or anything else. This is replacement. This is pyrrhotite and gold, which is replacing the magnetite, which is part of the banded iron formation. So what you can see here is a fracture. There's a fracture running along like that. It is full of sulfides, and it is cutting through the iron formation. And from the fracture, you can see here, replacing, and here is the front of replacement that you can see, replacing the iron formation coming out of the fracture is sulfides and gold, and here the rest of the iron formation is unreplaced magnetite banded iron formation. So it is quite clear that you can see very, very nicely in this image that there is hydrothermal replacement going on, at that this was not a syngenetic sulfide deposit, but is a replacement. And in fact, the replacement model is now the favored one, because there's lots of evidence for many other deposits like this elsewhere in the Archean, in Canada, in Tanzania, in Australia, where it's quite clear that in fact this is a structurally controlled replacement. Sometimes the structures are maybe bedding parallel, but in many other cases the structures are actually cutting across the bedding, and you can see that there is replacement coming out of these structures, and that the actual gold mineralization was introduced later by hydrothermal fluids reacting with the iron-rich host rock and producing sulfidation of the magnetite to form sulfides and together with gold. Another example that I can show you from Archean greenstone belts elsewhere in Africa, it's in Tanzania. The Archean Tanzanian craton is very poorly exposed compared to the Zimbabwean craton and the Kapwa craton, which have been uplifted and eroded recently. The Tanzanian craton has actually been depressed because the flanks have been uplifted in the rift valleys. So there's very poor outcrop, and that is why they don't have a historical mining industry like Zimbabwe, where they've been mining for 1,000 years. In Tanzania, it's only very recent mining exploration going on. But south of Lake Victoria, in the northern part of the Tanzanian craton, you have quite a number of greenstone belts. So this is called the Lake Victoria Goldfield. And in Africa, this is the third largest gold producer now in Africa, outside of the Witwatersrand Basin and West Africa, where you have the Birimian gold deposits in Ghana and Cote d'Ivoire and other places like that, Mali. The third largest gold field in Africa is here, the Lake Victoria Goldfield. And all of these gold deposits have actually been developed just in the last 2 decades. From the 1990s, mid-1990s up to now, a number of huge world-class deposits have been developed, including these ones here at Geita and Bulyanhulu, which have got resources exceeding 15 million ounces of gold per deposit. So very, very large deposits. And quite a number of other deposits have been opened up. There's been a gold rush here for the last 2 decades. More than 40 different companies have been operating here and trying to find ground. It's been a mad rush in this area, and mainly driven by the fact that you could find 1 or 2 very large, very rich deposits like Bulyanhulu. Bulyanhulu has got an average grade of about 15 to 25 grams per ton gold, and it's got gold plus copper, 1% copper, so it's a very, very rich deposit. I'm not going to go into details about it, but I will just show you some pictures. So this is one of the deposits, the Golden Ridge, where you can very clearly see there is an iron formation, and you have late cross-cutting structures. And associated with the cross-cutting structures, you get alteration zones where there has been replacement of the iron formation by sulfides. But it's quite clearly associated with cross-cutting structures. And the rest of the iron formation is actually magnetite. Here are some photographs of the Geita goldfield, just south of Lake Victoria. Lake Victoria is in the north there, and here is a ridge formed by banded ironstone, It's in the tropical zone, it's just a few degrees south of the equator. And these are trenches on the surface for the gold deposit at Gator. The host rocks are Archean greenstone belts, which are quite deformed, folded. You can see this underground photograph of the folded banded iron formation. And here we can see examples of sulfides replacing the iron formation, just as we saw in the examples from Zimbabwe. So this seems to be the style of gold mineralization that's associated with these various gold deposits. There's quite a variety of different deposits, whether they're hosted in volcanic rocks or banded iron formations, other sedimentary rocks like grey wackies, but they will all originate more or less from either metamorphic dehydration or magmatic deposits, channeled up by some structures and reacting with iron-rich rocks in the greenstone belts themselves. So, this class of deposits is also referred to as orogenic style gold. It's been in the literature now for a number of years, sort of the name that is bandied about. But you should just look at what is the actual, what are the controls. Don't worry about the labels. And try to understand what is actually happening in the deposit. Okay, so I'll stop there for this, and we can take some questions about this.
Thank you, Sharad. Agora nós temos tempo para algumas perguntas, se a audiência tiver alguma pergunta. A gente ainda está tendo problemas com a transmissão, infelizmente. Então vou fazer o seguinte. Nós estamos tendo problemas com transmissão para várias praças nesse momento. Então nós vamos parar 10 minutinhos entre a aula 5 e a aula 6, para ver se a gente consegue resolver esses problemas. Mas se vocês tiverem alguma questão para o professor, a gente aqui mesmo pode, nós que estamos aqui, podemos avançar com as perguntas, tá?
Bom, o professor mencionou o transporte e a deposição do ouro, mas eu gostaria que ele falasse um pouco da fonte, se possível, da geoquímica do ouro.
Okay, you talked about the transport and the source of gold, and we would like to know something about the source, the geochemistry of the gold.
Okay, I didn't have time to go into details about where the gold would actually come from, but if you look at the amount of gold that is found in crustal rocks, it's very, very low, less than 1 part per billion in average crustal rocks. But when you look at the Archean greenstone belts, you find that things like komatiites, for example, can have maybe a few grams per ton, a few parts per billion gold, and even maybe some of the mafic rocks might have one ppb gold. So they're still much higher than the average crust, which is very, very depleted in gold. What you need then is an efficient mechanism to transport the gold from a large volume of rock, which contains, say, 1 part or few parts per billion gold, and to then channel that amount of fluid into a narrow structure, so that you need large volumes rather than huge amounts of gold to start with. It's a very small amount of gold. You need large volumes of fluids channeled through a narrow conduit, some kind of fault structure, to bring it to the upper crust where it is deposited. But the source of the gold, in terms of the metamorphic model, if you like, it would be the greenstones. The other model, the alternative model, is a magmatic hydrothermal model, and in that case, the gold might be actually found in the magma itself. The magma is enriched in gold. There probably is. I think you find that the magmatic deposits have got an association, mineral association that might be more associated with say, granitic magmas, maybe a lot of tourmaline, and there's certainly a lot of subtle geochemical differences associated with that. I don't know how much work has been done on trying to differentiate magmatic versus metamorphic sort of sources.
Bom, eu não estou conseguindo transmitir. Eu não vou conseguir. Eu não prestei atenção na resposta. Desculpa, que nós estamos tentando resolver o problema da transmissão, mas eu acho que ficou claro para todo mundo, né? Mais alguma?
You mentioned that you have, for one greenstone belt, for the gold mineralization, you have a control as a gray wake. Is the main control, lithological control, metallotech that holds the gold mineralization. My question is, considering that in gray wake you don't have a lot of iron minerals, what would be the the control to in order to make the gold precipitates there? What's the control?
I think the ones that are found in the Victory group, the grey wackies there, are derived, they have very immature sediments derived directly from volcanic arcs. And they do have a lot of sort of volcanic rock fragments. And they might have iron, but I'm not sure if that is the main control in this particular case. There's a lot of wall rock reactions going on. That's in this latest study that I quoted. Another major important control is also the drop in temperature. So aside from reacting with iron-rich minerals, there are other reactions that are going on with wall rocks, and of course, as the fluids are coming up higher in the crust, there is also a drop in temperature, and that also destabilizes gold bisulfide complexes. So there's a whole range of mechanisms by which you can precipitate gold, and so it's not just iron as you find in the banded iron formations or in the basalts. That's not the only control on the formation of these deposits.
In that case, the sulfur will be always in the fluid first. The sulfur will be present in the fluid all the time because it doesn't affect the sulfur somewhere else.
Yeah. But the source of the sulfur is very likely from volcanic rocks. Volcanics will contain some sulfur, and the fluids will come up through there and will pick up sulfur. There have been some studies done where people have shown that metavolcanic rocks have been depleted in sulfur where the fluids have come through them, and you could do sort of mass balance calculations to say, well, this could be the source for the gold deposits that are higher up.
Okay, I think I speak in English because Sharad will have to know what's going on. We're having problems still with the transmission to elsewhere. So we'll have to give the people of the company some time for them to get things ready. So if you want to go on with the debates and questions, it's going to be all right. There's plenty of time. They probably need about 15-20 minutes to get it solved. So if you have any questions.
Stratigraphic terrains that had amalgamated to form the actual Kapwal craton itself. So on this newly formed continent, the Kapwal craton, which had stabilized by about 3.2 billion years, you formed sedimentary basin. Here it is in relation to the present-day geology of South Africa, and simplified version of that craton shows that it is made up of 3 blocks: the Witwatersrand block, the Kimberley block, and to the north the Pietersburg block. So these are 3 major crustal blocks that make up the Kafar craton. Now the oldest one of these is the Witwatersrand block, which contains, you can see on the east, the Barberton Greenstone Belt. Also, in the middle of it, you can see the Witwatersrand supergroup, or the Witwatersrand basin that is developed over there. The present-day size of the Witwatersrand basin, and we can see today, which I can show you here in this diagram, is actually a structurally preserved part of a much larger basin. This is structurally preserved, and so when you go back to this image, you can see that the outline of the Witwatersrand basin is in the central part, but to the east you have also the Pongola supergroup, which was similar rocks, same age, which may have been part of the same sort of basin. So this is the oldest part of the Kafar craton, this region where the crust had stabilized by 3.2 billion years, and on it the first sedimentary basin to form is the Witwatersrand basin, which at its very early stages has got a continental rift with volcanic rocks, which is known as the Dominion Reef. So the Dominion group, as such, is the sort of the proto basinal stage of the Witwatersrand supergroup. Now, the Witwatersrand is, of course, extremely important as the world's greatest gold field, and possibly 40% of all the world's gold that has ever been mined has come out of this one single basin. So it is of extremely great importance in terms of Archean metallurgy. So it is situated today around the city of Johannesburg, which is the biggest mining town in the world. And a lot of the Witwatersrand basin is actually covered by younger rocks. Within that circle, you can see in the southern part, it's the rocks of the Karoo basin, the Karoo Mesozoic rocks, and also rocks of the Transvaal supergroup and the Ventersdorp supergroups actually cover a lot of the Witwatersrand. So when you look at this map, it is actually a map of the subsurface, a sort of a sub-outcrop map of the Transvaal supergroup, of the Witwatersrand basin, if you remove the overlying cover rocks of the Transvaal, Ventersdorp, and also the Karoo basin. So in detail then, what you can see, a very significant feature of the Transvaal, of the Witwatersrand basin, is that in the center you've got the circular feature, which is the Vredefort impact structure. And the Vredefort impact structure has played a very important role in localizing and preserving the sediments of the Witwatersrand supergroup around it. So the Vredefort is dated at about 2020 million, whereas the Witwatersrand basin itself is 2.9 to 2.8 billion years in age. So the impact occurred very much later, but helped to preserve the basin around it. If the impact had not occurred, perhaps the whole basin would have been eroded away completely and would have not had it preserved at all. So, but it also helps to see a cross-section through the crust, because in the center of the Vredefort structure, you've got Archean granitic basement and granulites that are exposed there. So, in yellow colors on the west, you can see the rocks that make up the Dominion group, which are volcanic rocks, mainly felsic volcanic rocks that mark the beginning stage of the Witwatersrand as a continental rift phase. At the actual very base, on its contact with Archean granitoids, you find a conglomerate at the base of the Dominion group, major carbonate platform in Earth history, full of stromatolitic carbonates, and then transitioning into iron formations, which has some of the largest iron and manganese formations in the world of this age. So that's a summary of the cover sequences that we see at the Carpocraton, and then there's a huge unconformity, and then only 1.5 billion years later you find the Karoo supergroup rocks covering the rest in the stratigraphic column. So if we go around the city of Johannesburg, we see a satellite image on the right and a geological map on the left. What is exposed in this dome that you see is the pre-Witwatersrand basement rocks that make up the Carpocraton basement. And it consists of granitoids that are shown in the green colors, which have yet to be dated properly. There is no proper dates out of these. They are very mafic and ultramafic rocks with nothing that is datable in terms of zircons. They are intruded by lots of granitoids shown in the pink colors and the white colors. And the granitoids have, the intrusive ones are dated at between 3.4 to 3.2 billion years. The greenstones are older than 3.4 billion years. They are intruded by the granites. And that's what forms the local basement just in Johannesburg itself. It's actually the northern suburbs of Johannesburg are built on this very old Archean basement, 3.4 to 3.2 billion years. And then the Witwatersrand supergroup is overlies this lot unconformably. So here is the stratigraphy of the Witwatersrand. At the base, the Dominion group, dominated by volcanic rocks, with at the very base, the quartz pebble conglomerates with dominantly uraninite, but also minor gold. Then we have the Witwatersrand supergroup, or the West Rand group, with its different subgroups, dominated by quartzites and ferruginous shales with some ironstone. And then the Central Rand group at the top, which is the economically important ones, that has quartzites and conglomerates. And that's where the gold mineralization is found. And if you look at the ages, it goes from 3 billion years to 2.8 billion years. So when we look at the rock types, the West Rand group, dominated by shales and quartzites with some iron formations. There's also a thin mafic lava unit, which has given the date of 2.91 billion years. And then the Central Rand group with the important gold-bearing conglomerates and quartzites. So here we see a stratigraphic column showing the two sort of units. So there is a fundamental difference between the lower and the upper part of the Witwatersrand Basin. The lower part is a shelf succession dominated by fine-grained sedimentary rock shales with beautifully preserved sedimentary structures and quartzites that show herringbone cross-bedding, typical of tidal flat to shallow shelf kind of environments. The big difference is in the upper part of the Witwatersrand, the Central Rand group, where you have conglomerates. So there's a huge change in the energy of sedimentation. There is more proximal sedimentation happening in the upper part, where you've got quartz pebble conglomerates coming in and dominated by conglomerates and quartzites and no shales. So it is quite clear that there's something very dramatic that happens in the Witwatersrand Basin sedimentation, and it is in the upper part where you have the gold deposits. So that's something that you have to explain, what is happening in terms of the sedimentation. So the lower part, the West Rand group, is dominated by shales and quartzites alternating. But what you see here in black, in the lower part, the water tower slate, the contorted bed, is iron formations. And these are very thin iron formations that are, in fact, the very first shelf-type iron formations in the world. Previously, the iron formations that you found in Earth history were all associated with greenstone belts in a very different kind of a tectonic environment. The greenstone belt iron formations could have been forming in a back arc basin and associated with hydrothermal activity associated with magmatic arcs, whereas that's the so-called Algoma type iron formations. The other major type of iron formation that you find associated with the late Archean shelves is the superior type iron formations, which you find in the late Archean to early Paleoproterozoic, which is the kind of information you also find in Brazil, which are the more extensive shelf-type informations. But the Witwatersrand here at 3 billion or 2.9 billion has the oldest of these informations, which very thin, but they are in a stable shelf sort of setting. And in the upper part of the Witwatersrand, you have a whole series of these reefs. You can see the Carbon Leader, Main Reef, South Reef, Vaal and Basal Reef, Kimberley Reef, Ellsberg Reefs. All of these so-called reefs are conglomerates. They are packages of conglomerates. There are mainly quartz pebble conglomerates. That's another important feature of the Witwatersrand Basin. Although the basin rocks are sitting directly in contact with Archean granitoid basement, granites and greenstone belts, you do not find pebbles of greenstone lithologies or granites. You don't find any granite pebbles. All the pebbles in the Witwatersrand Basin are made of quartz or chert, very resistant rock types, or maybe sometimes jasperite, but not granites or greenstone. So there seems to have been some kind of a very important weathering cycle that precedes the source of the Witwatersrand detritus, because you are looking at something that is undergone weathering, and only the most resistant in the surface environment, the silica-rich pebbles, are the ones that are found in the reefs. And you do not find anything like the quartz or greenstone lithologies. So the reefs that you see in the upper part within the Central Rand group are the ones that are of economic importance. What I must point out is that associated with the main reef, you can see the Carbon Leader. The Carbon Leader is a carbon-rich reef. It has at the base of this reef a carbon seam that is maybe even less than a centimeter in thickness, maybe just a few millimeters, but it is very, very continuous and extremely rich in gold. That carbon seam, which might be a few millimeters thick, could be running at 200 to 500 grams per ton gold. So it is something extremely important to bear in mind, that a lot of the Witwatersrand gold is not only in the quartz pebble conglomerates, but also associated with carbon. So there is a dual association of gold with pyrite in the reefs and gold with carbon in these so-called carbon-bearing seams. So the great economic minerals of importance in the Witwatersrand Basin is gold, obviously. More than 50,000 tons of gold have been mined since 1886. That is an enormous amount of gold. That is 40% of the gold that has ever been mined in the entire human history in the entire world. So it is a phenomenal amount of gold that has been mined. In fact, you can change that figure now to probably closer to 60,000 tons. Also uranium, which occurs in the form of uraninite, and the uranium is a byproduct of the gold mining. It occurs in the same reefs as the gold, and there is also always a little bit of silver that is alloyed with the gold, so it's a byproduct, although the silver content would be maybe 1/10 or 1/20th of the gold, and in terms of value would be less than 1% of the gold, but it is still associated with gold. So you got three main economic minerals coming out of this basin. Okay, so let's look at the sort of the larger sort of tectonic setting, if you like, of the Witwatersrand Basin. And so we see the Kafar Craton, we see the Witwatersrand Basin right in the center of the Kafar Craton, and we see related lithologies such as over to the south and to the east, the Pongola. These have been found with either outcropping like the Pongola or from geophysics and drilling like these things in the south. So we have this extensive basin which had covered the southern part of the Kafar Craton with a shelf succession of quartzites and shales. But the conglomerates that you find in the upper Witwatersrand Basin are confined to this to the main Witwatersrand basin here, and in fact the gold-bearing conglomerates are all along the northern and the western margins of the basin, which are shown here in purple. This is where the different goldfields are. The Welkom goldfield, the Klerksdorp, Carltonville, West, Central and East Rand goldfields, and the Evander goldfields. All of these are the areas where the major economic deposits are found. There are no deposits in the southern part of the basin because there is a big fascist change. So the conglomerates are all associated with alluvial fans on the northern western margins of the basin, and the grain size reduces as you go down towards the southeast. So it appears that the Witwatersrand basin had an actively faulted margin to the north and the west. And you can see that in this diagram. There is a fault system here, the Rietfontein fault, and there is another fault system here around Kimberley and this one over here, which were active during sedimentation of the Central Rand group. So let's first look at the West Rand group, which is the shallow shelf. Here is the iron formation that I pointed out earlier. This is the famous contorted bed. It looks very folded, but it's only this particular bed that is folded, not the underlying or the overlying rocks. So it's almost a kind of almost soft sediment deformation. It's not quite, it's tectonic in origin, but due to differential movement between much thicker beds above and below versus this thinly bedded ironstone that you see here. In fact, this outcrop is taken at my university campus. It's about 100 meters from my office. So the university itself is actually built on this outcrop of lower Witwatersrand rocks. And here we see ferruginous siltstones in the lower part of the Witwatersrand. And you can see here in the Brixton Formation, beautiful flazer and lenticular bedding, which is what is typical of a tidal flat environment, ripples in a tidal flat. That's what makes up these rocks in the West Rand group. The Central Rand group, by contrast, is a high-energy environment with conglomerates and quartzites, and was formed in a contracting basin with deformed, faulted margins. And the interpretation has been that this is a foreland basin to some active orogeny that's occurring to the north and the west of the basin. So the environment then is basically an uplifted highland region to the north and the west with some active faults, which you can see here, and that produces a series of alluvial fans and sort of braided rivers coming in to a body of water. And these sediments, they get reworked. The conglomerates that are being carried by these rivers actually get reworked along the margins of this body of water. And there are clear facies changes going from conglomerates into quartzites as you go in this direction. So these are the quartz pebble conglomerates from the upper part of the Witwatersrand basin. This is in the Turfentine subgroup. You can see beautiful beds of conglomerates alternating with quartzites. Here are the quartzites, and you can see the conglomerates in the background interbedded with them. So a high energy environment, typical braided river conglomerates and quartzites with trough cross beds, planar cross beds, fluvial sort of sediments. This is the discovery place where the actual outcrop of the gold-bearing conglomerate was discovered by prospectors in 1886. There was somebody called George Walker and George Harrison, two prospectors who stumbled upon this outcrop, and they panned it, and it was very rich in gold, and that was the start of the entire Wits gold rush. And shortly thereafter, the founding of the city of Johannesburg. So here we see quartzites interbedded with the conglomerates, and you see the white color here is from the oxidation of pyrite. The pyrite is converted to iron sulfate and producing the white colors that you see on outcrop. So this is a photograph taken underground where you can see the typical conglomerates interbedded with quartzites, and there are dominated by quartz pebbles. And aside from the quartz pebbles, there's also a lot of pyrite that makes up these conglomerates. So here we see a photomicrograph that shows quartz pebbles and lots of pyrite. But notice that the pyrite is actually very rounded grains. They are actually detrital pyrite grains. And the rounding actually cuts across the banding in the pyrites. Some of the pyrites show crystallographic banding, which is transected by the round surface of the grain. It is very clear that these were pyrite crystals of some sort that were rounded by detrital rounding. There are also, you can see occasionally, like some of these more shiny grains which are recrystallized. They have euhedral outlines, but they are clearly of metamorphic origin due to later events. So this is important. You have quartz pebbles, which are indicating that there is a mature source, no granites, and we have pyrites, which are telling us something totally different. There is some source of pyrite out there in the depository, in the source rocks, and the atmosphere was reducing, because otherwise the pyrite would not have been outcropping, it would have been oxidized. There was actually zero oxygen in the atmosphere at this time. We know that from the multiple sulfur isotopes and so on, which I'll discuss later on. And it is quite clear that this pyrite is of detrital origin. A vast amount of the pyrite is detrital in origin. And here in this photomicrograph, you can see rounded detrital pyrites, but you can also see gold over here. This is gold, but the gold is interstitial to the pyrites. This is actually secondary gold along some fracture, where the gold is now coming in along a little vein, and it's occupying the spaces between the pyrites. The gold is hydrothermal. This is, but this is what most of the gold actually looks like. If you take any typical gold-bearing sample from the Witwatersrand reefs, this is what you see. The gold is secondary. The gold is in fractures, and if you liberate the gold, the crystal forms are dendritic and very different from detrital gold. The pyrite itself is very clear that it's rounded, but the gold not. The gold has clearly been recrystallized. So this is part of the big problem. The Witwatersrand, as you will understand by the end of this lecture, is not only is it the largest gold deposit on Earth, it is also the most controversial in terms of understanding its origin. And it has been like this from the very beginning. In fact, back in the 1890s, a French professor, very famous Professor Louis de Launay, who was a professor at the School of Mines in Paris, he spent 3 months visiting all the gold mines in the Witwatersrand, then wrote a book about it in French. And he discussed already that there were 3 theories about the origin of the gold. 1, it was detrital in origin. 2, it was hydrothermal in origin. Or 3, it was actually precipitated at the same time as the sedimentation. So there were 3 theories about gold, and he could not decide even then which one to support, because there was conflicting evidence always. You know, if you say it's detrital, how do you explain this kind of textures? If you say it was modified, how do you explain some other textures? And so on. And those arguments have been going on right up to the present day. So this is one of the interesting things about the Witwatersrand Basin. Almost every other class of mineral deposit, we have solved the origin problem. You know, we know how porphyry coppers are formed or how iron formations may form. But the Witwatersrand gold deposit, the biggest of them all, we're still arguing about it. So here we see the gold fields that I shown you before, shown in the gray colors, all along the northern and the western margins of the basin. So here is some ideas about how these deposits actually formed. So we see, say, an area of uplifted terrain with a lot of alluvial fans forming along the margins. And here is an artistic depiction of what the Witwatersrand rocks would have looked like during deposition of the Central Rand group. So we see these faulted highlands, and in cross-section you can see some faults, and alluvial fans coming off these faulted regions ending up in a body of water. So the conglomerate reefs are supposed to be coming from these bedded river systems along these alluvial fans, and that's what's bringing in these conglomerates, alternating with quartzites. But the important thing to note about the Witwatersrand Basin, that it is not just a normal fault. It's not a single fault system that's bounding the basin like you find in rift systems. This is not a rift. This is an actively faulted basin margin which is undergoing contraction. There's in fact a lot of evidence for even overturning of the beds. I'll show you some cross sections on the margins of the basin. And notice what is happening here. Here is a quartz reef. If you follow the arrow, there is a quartz reef here which is now truncated. Sorry, let me just go back. It is truncated by a younger reef. So you find that the earlier formed reefs are uplifted and then truncated by younger reefs, and this younger reef itself is being truncated by yet another younger reef which cuts several older reefs. So this process is going on the basin margins. There is a conglomerate that is formed, but it is then uplifted and cut by another conglomerate, and that conglomerate itself is uplifted and cut by another one. So there is continuous reworking of older deposited conglomerates by younger ones. And that process is enriching the later conglomerates into title minerals, heavy minerals like gold and uranium and so on. So this is a sedimentological process of getting very high grades. This is one way that the sedimentological model, the detrital sort of model for gold, can explain why you have such high gold grades. Because it's not just a huge amount of gold in a source area which is brought and just deposited in one place. It could be small amounts of gold, but it's being concentrated and concentrated in the same place by subsequent unconformities and what we call cannibalization. The younger reefs are eating away the older reefs and cannibalizing them and concentrating the gold at the same time. So that's one process that is definitely happening along the basin margins. And here are some very impressive diagrams that show that along the margins of the gold fields there is uplift and even overturning of the beds. So there is active faulting. Here in the Welkom goldfield, these Witwatersrand rocks have actually been overfolded like this by faults. And here in Johannesburg itself, you can see the beds which are dipping to the south are uplifted until they are vertical and even overturned in some areas of Johannesburg. And then there's normal faulting associated with that. So there's clearly compression going on the margins, the northern and the western margins of the Witwatersrand goldfield, and active tectonics during sedimentation, uplift during sedimentation, which is resulting in this concentration process. So this is the part of the modern city of Johannesburg. It's not the whole city. It just shows you the extent of the mine dumps which used to be present around Johannesburg, and they have now all been retreated and to recover gold for the second time. And now the Witwatersrand goldfields are more than 130 years old, very, very mature, and in fact they are reaching the end of their lives because most of the gold mines are now marginal economically. The cost of mining so deep is so much that it's very close to the current gold price. Therefore, they cannot actually be mining at a profit. And so if the costs keep on rising, especially labor costs as happening in South Africa, and the gold price is very low, then most of the mines will have to close. But it's a matter of economics. I mean, if the gold price, if South Africa stops mining its 300 tons of gold every year, the gold price is going to go up. And so it's kind of a self-buffering system. It's always protected the South African industry, actually. Whenever it's in trouble, the gold price goes up and then it gets out of trouble again. But the problem is that the amount of gold that's been mining has been declining. For the last 2 decades, it's been declining, and it's at its height. South Africa was producing about 900 tons of gold every year, and it has come down to now less than 300 tons, maybe 250 tons, and decreasing. So that's a problem. However, it still has the world's largest gold resources. If you look at this map, all the areas that are shown in red are areas that have got huge gold resources that are known, future resources, but they are very deep, except for the ones here in the Sun Target area, the northern extension of the Free State Goldfield. The other areas here are deep gold resources, which will cost even more to mine at depth. But the resources, it's been estimated that in this area here, there's still another 30 million ounces of gold. Sorry, not 30 million ounces, 30,000 tons of gold still there. 50,000 tons have been mined up to now in 120 years, but it's estimated that's probably still another 30,000 tons underground. Now, you cannot mine all of that stuff. It may be underground, but if it's in a very thin reef, it's not economic to mine. So it's a resource that will be there, but it's just a resource. It will never be a resource in an economic sense. It's just gold that we know about. But things can change dramatically if we change the way we mine gold. And this is what is going on in South Africa now. There is research going on in South Africa to do very deep mining using robot technology. So it's very dangerous to mine at such deep levels because it's very expensive, and there is a danger from rock bursts because of the high pressures. When you're mining at a depth of 2 kilometers underground, and the deepest mine is actually 3.5 kilometers, that's the deepest mine in the world, where the rock face is at 65 degrees centigrade. And you have to refrigerate water to pump down and to cool down the rock face before people can actually work in that environment. It's very dangerous, especially at the drilling phase, because that is where rock bursts occur all the time when due to release of pressure. So the working phase is the most dangerous, and the further down you go, it's more and more dangerous. So the biggest problem with deep mining is the cost and the safety issues. But if you can mine without people, and you can use robots, then perhaps you can also mine thinner reefs and mine it more economically. So the CSIR in South Africa are doing research in robotic mining, and they have already got prototypes which look like little cars, the electronic sort of cars. They have prototypes that they have already worked. They are fully equipped with sensors, infrared and cameras and whatever, and they can be mining small reefs and use ultrasound for breaking rocks. You can have little thing that instead of using explosives, you can use ultrasound, and then a whole fleet of these things operated by somebody on surface who's a little boy grown up playing with little toys who can have a whole fleet of these little vehicles that just remove the reef. The reef might be 10 centimeters, and you can mine that, and you just go in and extract that. And perhaps this will be the future of gold mining in another 50 years or so. So perhaps there may even be a period when all the mines will close completely, because it'll just be too expensive to mine compared to the cost of mining. But the technology is being developed to perhaps reopen the mines and extract some of this 30,000 tons of gold that is still underground. So that is the future of Witwatersrand gold mining. It will probably be mined by computer geeks rather than by geologists and mining engineers. Okay. So overlying the Witwatersrand supergroup is the Ventersdorp supergroup, which is the outpouring of major volcanic rocks covering the whole Kapwa Craton at some point. So here we see the Witwatersrand Basin in its preserved sort of outline here. And to the west, we see this huge area of Ventersdorp flood basalts. And these continental flood basalts which covered that whole western part of the Kapwa Craton. Now here is a stratigraphy of the Ventersdorp, and you see volcanic rocks, we see some sedimentary rocks together with felsic volcanic units like here, and then more volcanic rocks near the top. So it's dominated by volcanic rocks. But if you look at the very base of the Ventersdorp, shown here in this red line, which is much thicker than the actual deposit itself, is a quartz pebble conglomerate called the Ventersdorp contact reef. It's on the contact between the Ventersdorp supergroup and the underlying Witwatersrand basin. And this is another rich gold uranium-bearing quartz pebble conglomerate, which is mined economically. So we have seen at the base of the Dominion, right overlying the Archean basement, Archean granitoid and greenstone basement, you have a quartz pebble conglomerate with uranium and gold. Then you have the Witwatersrand basin with its, in the upper part, lots of reefs with gold and uranium. And then in the base of the Ventersdorp, we see gold and uranium as well. So these are the lithologies, but the only ones of economic interest, as I said, is right at the base where you find this Ventersdorp contact reef. And in fact, you can see it in this photograph here. This is from drill core. This is the upper Witwatersrand sediments, and the reef here in this drill core is a pebble reef with quartz pebble conglomerate, and it's overlain by mafic volcanics of the Ventersdorp lavas. So it is this reef a few meters in thickness, which contains gold and uranium. So during the middle Ventersdorp times, the volcanic rocks that are shown in green colors, the flood basalts, are block faulted, and there's a lot of extension going on, during which you have sedimentation with alluvial fans and lacustrine sedimentation, and even some stromatolites have been found associated with these sediments. And there's an outpouring of felsic volcanic rocks marking this phase of rifting during the Plattberg group times, and then the whole lot is overlaid by more mafic lavas. So the Ventersdorp marks a major extension event of the Kapwa Craton, where perhaps it may have even halved in its crustal thickness from a crust that may have been about 60 kilometers thick to probably about 45 kilometers in thickness. And here is a cross-section through the Free State goldfield, which shows one of these kinds of Horst and Graben structures formed in the Plattberg times. Here we see the Witwatersrand supergroup, the West Rand, Central Rand, overlain by the lower Ventersdorp mafic volcanic rocks, and then the whole lot was faulted with a Graben and a Horst, and this kind of sedimentation, and then overlain by more volcanic rocks at the end of Ventersdorp times. So these are the kind of volcanic rocks with which the Ventersdorp ends. The Ventersdorp is then overlain by the Transvaal supergroup, and if you look at this this diagram, it shows the imagery taken from seismic sections, vibro-seis images which were done in the 1980s, and from the seismic data we can see that there are these little grabens that are shown in red here of Ventersdorp age, overlain by a continuous layer like a basin of the Transvaal supergroup. So these black and blue rocks followed by gray and yellow rocks, this is the Transvaal supergroup which overlies the rifted Ventersdorp. So the interpretation is that it's a kind of a rift sag basin. Initial rifting of the Ventersdorp overlaid by thermal subsidence, and it's a thermal subsidence basin in which you have quartzite and a carbonate platform developing in the Transvaal supergroup. Now, at the very base of the Transvaal supergroup, you find what is called the Black Reef. It's another quartzite and a quartz pebble conglomerate again, with pyrite and gold. And it's also being mined even up to today. So the Black Reef is at 2.6 billion years, and we saw that the base of the Dominion group was 3 billion years. So this Witwatersrand supergroup and the overlying rocks and the underlying rocks form a series of supercrustal basins overlying the Archean Kafar craton, and it's 400 million years of sedimentation of quartz pebble conglomerates with other sediments, and there is mineralization in the Dominion Reef, in the Witwatersrand Reefs, the Ventersdorp Contact Reef, and in the Black Reef at the base of the Transvaal supergroup. So continuous sedimentation for 400 million years with mineralized quartz pebble conglomerates with gold and uranium. So the evidence from this is that there was a reducing atmosphere to allow for titral pyrites, titral uranianites, and somehow the gold is part of the story. So this is what I will be talking about in the next part of my story. Let me just finish this part at least to say, well, if you interpret the tectonic setting of the Witwatersrand Basin, then this is a story that was published in our book that I showed you yesterday, The Story of Earth and Life. And this is because our main editor of that book, Professor McCarthy, published a paper some 20 years ago in which they had this model that the Witwatersrand Basin is forming as a kind of a foreland basin in relation to tectonics that are occurring as a result of the collision between the Zimbabwe craton and the Kafar craton. And this model has been repeated many times, including in the new textbook on South African geology, which was published in 2005, or 2007. There is, however, a problem with this model. It doesn't work. It is wrong. Now, why is it wrong? It's wrong because if you remember what I talked about yesterday, when I talked about the Zimbabwe craton, I said to you the Zimbabwe craton was formed at 2.6 billion years ago by the major granitic event. But the Witwatersrand Basin is deposited 2.9 to 2.8 billion years ago, at a time when the Zimbabwe craton did not exist. So this model has to be wrong. It has to be. It was not possible for the Zimbabwe craton to collide with the Kafar craton because it didn't exist. So, but when you look at the sedimentology of the Kafar craton, it's clearly a foreland basin. The northern margin, the western margin are deformed. The basin was shrinking. There was active tectonism. So something collided to the north and the west. But whatever it was not the Zimbabwe craton. In fact, now we understand, with more research in the last 20 years, we understand what was responsible. It was, in fact, those other blocks that I showed you in that map earlier, the Petersburg block, the Kimberley block to the west of the Witwatersrand block. These blocks were colliding, and we now have the age of the collision is around 2.9 billion years. There are greenstone belts that are forming there between 3 and 2.9 billion years in the west, near Kimberley, and also this northern Petersburg block. There is a greenstone belt here, the Murchison greenstone belt, which is forming as a result of this collision. So it is these other terrains, the Archean terrains, that are colliding at the same time as sedimentation going on in the Witwatersrand block. So this is what is actually responsible for the Witwatersrand foreland basin. So what we now have to think about in terms of trying to think about the origin of the gold, if the gold is detrital, it must be coming from magmatic arcs, which are the greenstone, represented by greenstone belts here and to the north. Those greenstone belts actually coeval with the sedimentation in the Witwatersrand Basin. So this is something we have to bear in mind. We have to find a source of active, sulfide precipitation to produce the pyrites that we see that are now detrital pyrites in the Wits Basin. And there are a number of other things that we have to take into account. Yesterday I showed you evidence that there is a glaciation in the lower Witwatersrand. What did that glaciation have to do with the story? We don't really know. Nobody has really studied that problem, the link between this glaciation, followed by perhaps some very intense weathering, because we see only quartz pebble conglomerates. We don't see any granite pebbles. But in Johannesburg, the Witwatersrand supergroup is sitting directly on Archean granites, but we don't see the pebbles. Why? There must have been a lot of weathering before the sedimentation occurring to provide the quartz pebble conglomerates and not any pebbles of granite. So this is the sort of model that we have for the Witwatersrand block, the Petersburg block, Kimberley block. You can see these greenstone belts here, the Krypan and the Stella greenstone belt. They actually have Archean lode gold mineralization in there. There is also gold mineralization in these greenstone belts, the Murchison, Petersburg, Guyana greenstone belts, and they were forming at the same time as the Witwatersrand Basin. So the only basin that is pre-Witwatersrand, the only greenstone belt, is the Barberton one, and the one in the Johannesburg Dome. The other greenstone belts of the Kava Craton are actually coeval with the Witwatersrand block basin. They were forming at the same time as this basin was forming. Okay, so maybe we should have a short break here before we continue with the next part, which would be the origin, discussing the origin of the Witwatersrand. So I've set you the geological framework of the Witwatersrand and its tectonic setting, if you like, and then we can go on to discuss the origin. So if there are any questions now about the Witwatersrand itself.
Se houver alguma pergunta agora daqui da audiência, senão a gente vai parar e volta 1h10 por aí, depois do almoço. Há alguma pergunta? Alguém quer fazer alguma pergunta? Ah, será que ele conhece? Vamos perguntar. You know the moeda formation in Brazil? Yes. Você pode informar um pouquinho mais para ele, sim, sobre? Well, that's more or less the same sort of associations, gold and uranium. It's called the Moeda Formation, and it's.
What is the age?
Qual a idade? Arqueano? What? Yeah, that's right. Yeah, but I know about that.
I think. Yes, look, there are a number of other places in the world where there are quartz pebble conglomerates with gold, even uranium. There's Blind River in Canada. There is Birmian in Ghana, the Takwayan, and these ones. Is this Jacobina that you're talking about, a moeda? Uh-huh. Yeah. Okay.
It's the base of conglomerate, has gold, has uranium.
Right. Yeah.
And a lot of pyrites.
Yeah.
And over-utilized supergroup minerals.
Right. Okay. Okay. So Paleoproterozoic. Yeah. Right.
Some difference that we have not on this sequence and don't have any more auriferous conglomerate.
Right, just the basal one, yeah. So this is what you would expect to find if there was, just a placer deposit eroding a basement that already has gold mineralization in it, you expect to find this kind of a deposit with detrital gold and so on. And if it was in the Archean or early Paleoproterozoic, you would find uranium as well, detrital uranium. And you find this in many other parts of the world. There is in fact a report that was done at the Carnegie Institution, an entire book on other quartz pebble conglomerates with gold in them. So there are quite a number of them. They're also in Russia and other parts of the world. Only problem is that they are just confined to those basal conglomerates, and you do not find repeated things, and you do not find the continuity and the depth and the great extent and the grades of the Witwatersrand. The Witwatersrand is unique in that respect, but it's, as you can see, it's also a foreland basin. It's not just some successor basin. It's clearly got active tectonics during sedimentation, and there are still big questions to be answered about the origin of not only the gold but also the pyrite. Maybe the uranium is easier to understand as being detrital. We have already done some work on the pyrites, which shows multiple origins for some of the pyrites in terms of sulfur and iron isotopes.
Traduzir você entende mais sobre isso? Quer traduzir mais ou menos o que ele falou para a gente escutar? Traduzir a resposta? Não consegue? Traduzir a resposta dele, não? Não, tudo bem. É, eu entendo.
Desculpa. Não. O que ele falou foi o seguinte: em vários lugares do mundo. Ah, tá. Da gravação, ok. O que ele falou foi que em vários lugares do mundo há situações similares, onde você tem um conglomerado basal, aurífero, também com urânio, mas você não tem nessa sequência sedimentar que está sobreposta a esses conglomerados basais, em lugar nenhum do mundo, em geral, você não tem os outros níveis de conglomerados. A evolução é completamente diferente. Ele está falando que, no caso, Witwatersrand é tipicamente uma bacia de antipaís, né? Que não é o caso da maioria desses conglomerados. A evolução tectônica é associada com os conglomerados basais. É isso que foi a resposta.
And is there any relation? Is there any cause and effect associated with the different ages? I mean, these are Archean and the other ones are Paleoproterozoic. So, is that a geological process that would be different from one place to the other? Or it's just a tectonic control?
I don't really know the answer to that question, because what is different between the Archean and the Paleoproterozoic or the later Proterozoic is of course the difference in the atmospheric composition. Yeah. So if you look at, say, the Takwayan in Ghana, where you have quartz pebble conglomerates, but they have no pyrite. They have iron oxides, but no sulfides, right? And to what extent that difference is significant, I don't really know, because there is another problem: is what is the role of bacteria in all of this? This is something that is being currently investigated for the Witwatersrand gold. I will talk about it now when I talk about the origin of the gold, but we can also discuss it afterwards. But that's another problem if there is a change between the Archean and the Proterozoic.
Eu perguntei se tinha alguma influência também pelo fato delas serem arqueanas e paleoproterozoicas, né? Mas ele disse que não sabe responder assim, se tem alguma diferença em relação a interações com a biosfera e a atmosfera e tal. Tranquilo, né? Tá ótimo, então. Beleza, ótimo, então. Mais alguma pergunta, pessoal? Não? Então vamos almoçar e a gente volta 1h10, 1h15, pode ser? 1h30? Já são meio-dia e 30? Ok, 1h30 então a gente retorna, ok? Obrigado.
Tons of gold have been mined out of this basin since 1886. It's maybe 35-40% of all the gold that's ever been produced in the world. And you can see historical production. Historically, in the 20th century, South Africa dominated world gold production. And you can see that they used to produce half the world's gold. And sometime in the 1960s, when they reached the peak of their South African production, they were producing probably close to 70-80% of the world's gold. And but since reaching that peak in the 60s, there's been a major decline in South African gold production annually. And at its peak, it almost reached 1,000 tons a year. It has been declining ever since. And by today, it's roughly around 250 tons. So, and the rest of the world's production has taken over, and South Africa lost its place from being number 1 gold producer in the world to being somewhere around number 5 by now. It's been overtaken by China, United States, Australia, etc. So this was the all-time world gold production, and you can see how important the Witwatersrand Basin has been in terms of total world gold production. The Greenstone Gold has produced maybe 20% of the world's gold, but and then there are all the other types are important, but Witwatersrand by itself accounts for a big chunk, 1/3 or more of the total gold production in the world. So it's something very, very important. And how did it all start? Well, back in the early 1880s, there were these two brothers, Fred and Harry Struben. Here they are. Well, there's Fred Struben, and then they had a small little gold mine working on quartz veins. This is not a Witwatersrand type deposit. It's kind of related to the Wits because it's related to faulting in the Wits, but the host rocks are actually the Transvaal supergroup quartzites to the west of present-day Johannesburg, and they had a small stamp mill which was operating. It was the only one in the entire district at that time, and they had a guy called George Walker who was working for them, and he was prospecting in the general district, and it was George Walker who then stumbled upon the outcrop of the Witwatersrand conglomerates. He took it back to their little stamp mill and crushed the ore, panned it, and found the rich gold, which led to the discovery of the Witwatersrand goldfields. So Johannesburg, shortly after the discovery of gold, was a tent village with huts and tents, and it soon became, it started growing with a few brick buildings by the 1890s, and became the modern metropolis that you see today. So, and in here you see in the background these big mine dumps from the earliest phase of gold mining in the Witwatersrand. This photograph was taken maybe some 20 years ago. Those mine dumps don't exist anymore. They have been removed by reprocessing to remove all the extra gold that was found left behind. This is an early picture of a battery of stamp mills from the original gold mines, and a few of them are still existing today. Now, this is one of the earliest gold mines in Langlaagte, near the discovery site in the 1890s. And today this is what a modern Wits gold mine looks like, close to Johannesburg, near the town of Carltonville. And you can see the shafts in the background here. These shafts go down 2 kilometers down, and the deepest mines are the deepest mines in the world at 3.5 kilometers depth. So here is a satellite image of Johannesburg, which is a city that has grown around the mine dumps. It is, in fact, its origins of Johannesburg is as a mining town. It's the biggest mining town in the world. It now has a population of somewhere like 4 million people. So that's the origins of this great city of gold. Here is one of these modern mines, the South Deep, which has a resource of somewhere around 80 million ounces of gold. So it's still a huge, huge mine, and they're going very deep to extract all these resources. If you go underground, you can see these conglomerates integrated with quartzites. And what is very interesting, which I've not mentioned before, is that you do find a lot of alteration associated with these quartzites. Here we see pyrophyllite. It is a phyllosilicate. It looks a bit like chlorite, like a mica. It's a low-grade metamorphic mineral, and it's found in the altered quartzites associated with gold-bearing quartz reefs. So here's a quartz pebble conglomerate. You can see all kinds of features, including some possible pressure solution between quartz pebbles and so on. And here at the in one of these conglomerate reefs, you can see at the base of the reef actual grains of visible gold. You can see here, this is actual gold. The rest of it is pyrite and quartz pebbles in this very thin reef. So it may be a very thin reef, but it's running at very high grades. So because of the requirement that, because people are mining these reefs underground, there is a minimum mining width of 1.2 meters. So even if your reef is 10 centimeters in thickness, it could be running at 150 grams per ton. You will have to dilute that down to 1.2 meters and at 10, say, or less than 10 grams per ton in order to be able to mine with humans. And as I said earlier, maybe the new technologies will enable you to mine just the reef alone without mining any waste. So this is the Witwatersrand Basin with the outlines of some of the major gold deposits shown in red. The different gold fields, the Evander, the East Rand, Central Rand, West Rand, Klerksdorp, the Carltonville, and the Free State gold fields. And just to remind you again of the stratigraphic column, we have the Dominion group at the base with a quartz pebble conglomerate right at the very base with gold and uranium. The West Rand group, which is a shelf succession with no gold, but in the Witwatersrand, but the Central Rand group with lots of conglomerates and lots of gold-bearing horizons. Then you have the Ventersdorp supergroup at the base, gold-bearing reef as well. So here is again a schematic diagram showing where all the gold and uranium is concentrated in the Central Rand group. So this is kind of a schematic diagram what the landscape would have looked like. There was no plants, of course, only bacteria. We know that I showed you evidence yesterday. There were algal mats, there were microbially induced sedimentary structures on these, so they certainly were colonizing the sort of shorelines, but there's sediments and there's gold. And the big question is, where does the gold come from? Now we can look at similar environments today, such as a braided stream environment, where you have a channel, you have a sand and gravel bars and point bars like this, and also mud in the overbank environments. And we can look at where gold might be situated in those kinds of environments. But that's the interpretation of the sedimentary environments for the Witwatersrand sediments in the upper Witwatersrand Central Rand group. So here we see these, again, quartzites and conglomerates, a nice cross-bedded quartzites. And here underground you can see a cross-bedded quartzite which has a pebble lag at the base, and then it's graded upwards. There's another pebble horizon and so on. So you can see that the pebbles are forming in fluvial channels. On the bottom of the channels is where you're forming some of these pebbles. So here is an interpretation from the work of Laurie Minter for the sedimentary depositional environment in the Welkom goldfield. So you had this uplifted terrain with braided rivers and these kinds of alluvial fans, but on the shores of some body of water where these conglomerates are being reworked in a nearshore environment. And according to this interpretation, you also had algal material, these algae forming on the shorelines. I showed you this photograph a few pictures ago here, where you see the algae on the shorelines. That algae is interpreted in this as having formed carbon seams. But this is controversial. I'll show you what the carbon seams are. The carbon seams are a very important component of the whole Witwatersrand system, because up to 40% of the Wits gold is actually associated with carbon rather than with conglomerates only. So that was part of this whole story. So we have to ask the question, how did this rather ordinary looking sedimentary basin, ordinary in the sense that all the processes that we can see, all these sedimentary structures and so on, are very common in other basins elsewhere, fluvial environments, conglomerates and so on. How did such an ordinary looking sedimentary basin accumulate such a phenomenal concentration of gold and uranium? You're talking about 40% of all the gold in the world. How did that end up in one basin? And so this is, in fact, when you ask such a question, this is the biggest unsolved problem in economic geology. It really is the biggest mystery in economic geology. And as I've already mentioned, there have been several schools of thought originating from the 1890s. There were 3 schools of thought, and they've became, by 1905, 1910, became basically 2 schools of thought: the placerist school and the hydrothermalist school. The placerists believe that the Witwatersrand ore deposits are placer deposits, heavy mineral deposits, derived from something older that has been eroded. The gold is derived as a placer mineral. The hydrothermalists believe that the gold was introduced by hydrothermal fluids after sedimentation. So let's look at the evidence. What is the evidence for these 2 models? So the placer model, firstly you can see that the gold tends to be very, very confined to these particular conglomerate layers. You will not find gold, on either side of a conglomerate layer, but just confined to that particular pebble bed. And the best evidence has come from just this particular specimen. It's just one individual specimen, which is in the collection of the University of Cape Town. This is extremely rare to find in the Wits Basin, but this rare find has given us clues about the origin which nobody can contest. And what you see here is a conglomerate overlying coarse-grained sandstone. And the sandstone, the top of the sandstone is cross-bedded, and on the cross-bed sets, on these heavy mineral layers, is gold. This is all gold, not pyrite, but gold. And so this was regarded as sedimentological control. Now, you can see something like this also when you look at strata-bound copper deposits. You can see cross-bedding with copper sulfides along the heavy mineral layers. But that is formed by replacement. That's not formed by detrital copper sulfides. So what is the argument against a replacement origin for this gold? Why is this gold not replacing something that was along this cross-bedding and chemically replacing it? Well, what Professor Laurie Minter, who did the study, what he did was he took a slice of this gold from the specimen, and this is the remaining part of the specimen. So the other half of the slice, he dissolved it in hydrofluoric acid to liberate the gold particles. And then he examined the gold particles under a scanning electron microscope to see what they look like. So here is one of his images. This is a scanning electron photomicrograph of a gold grain out of that particular specimen. And this looks like a pizza. You know, there is a particular kind of pizza where they put a sausage around the rim. Well, here, the rim has been overfolded. If you did a cross-section across here, like this, you find that this portion has been overfolded. And so it's a very peculiar shape of a gold grain. It is rounded in one direction, but it's kind of overfolded. And there are other examples of these morphological types. So there are two morphological types of gold in the Witwatersrand reefs. There are these rounded grains and these very crystalline looking grains, very irregular shapes, which is what the most typical gold looks like. The vast majority of gold in the Witwatersrand looks like the stuff on the right because it's recrystallized. But in that one specimen from the Welkom goldfields, Professor Minter found these rounded grains. Now these rounded grains are actually very typical of the appearance of alluvial gold. If you look at gold from placer deposits, because the gold grains are very malleable and they are knocked around by silicate grains, they fold over into those shapes. And that is the exact shape that has been found in that particular specimen, and the gold is concentrated along the cross-bedding. So there is no question that that particular specimen, the gold was detrital. It was actually detrital gold sitting on the cross-bedding surfaces, whereas in most of the other gold, it has this kind of a shape because it is recrystallized after it was deposited. Now the other major association of gold, aside from being in these gold-bearing conglomerates, is the association with carbon reefs. And about 40%, that's a very significant amount of Wits gold, is actually associated with carbon. And in this paper by Mossman et al., they basically showed that carbon is actually indigenous to the gold. It's not something that was brought in from outside as a hydrocarbon, a mobile hydrocarbon, which is what some people have suggested. They think that these are actually the remains of algal material filament. It has a filamentous structure when you look at it under a scanning electron microscope, and they think that this carbon was helping to trap the gold. Now the gold could have been physically trapped by algae on the surfaces, or perhaps chemically trapped as well. But there is certainly a huge association between gold and carbon that you see here. Now here are also some photographs where you can see some of these carbon seams, very, very thin, just a millimeter thick. It's called bitumen over here and over there. But there's a lot of gold associated with these very, very thin carbon seams. And the rest of it, you can see lots of pyrites, which is very typical of the most of the conglomerates. Sometimes there is heavy gold concentrations on the bottom, but in other parts it may also be on the top. It varies, but it's not just evenly distributed throughout. There seems to be either a very strong sedimentological control or some control in terms of where the carbon seams are found within a reef. The other thing to note is the shapes of some of these pebbles. They're not all perfectly round. This one has been interpreted as a ventifact. That means a pebble that has been affected by wind-blown sand, which affects the faces, polishes the faces on one side. This happens in desert environments, and this is one interpretation of what's some of the processes going on in these conglomerates. Here we see a close-up of one of these conglomerates that's full of pyrite. These are 2 layers of pyrite. And when you look up at this portion here, in close-up, you can see, for example, this grain here. This is one single rounded pyrite pebble. It's a huge pebble. It's about 1 centimeter across of just pyrite. So somehow you need a source of fairly massive pyrite, big pyrite crystals, maybe even a massive sulfide that is eroding to form these kinds of pyrite pebbles. So according to the placer model, then, the gold is somehow derived from some pre-existing gold-rich mountainous terrain that by physical erosion, and the rivers that are bringing in the pebbles are also carrying the gold as a detrital particle. So if you are doing that, and the pebbles, the quartz pebbles, are being carried by the same water that is moving at a certain velocity, then you can apply some of the fluid dynamic sort of models on how sediments, particles of different densities can move in water. And we know how gold is always concentrated in potholes on the bottom of rivers, because gold is so dense, compared to quartz. Quartz might have a density of 2.6. Gold, with a density of about 16 grams per cubic centimeter, will tend to concentrate in these sedimentological sort of areas, and somewhere maybe in between some of the particles. Now, if you look at how heavy mineral deposits form in a river environment, like say a braided river where there is a change in direction of the river flow, wherever there is a change in direction, then some material is deposited on one side and is eroded from the other side of the river channel. So the places where there is deposition are places where the flow velocity of the flowing river is below the critical velocity needed to move a particular grain size fraction. And so this is where you get deposition. So when you look at a deposition like that, because it depends on the flow velocities, and even a slight decrease in flow velocity will drop out the most dense materials. So right on the edge of one of these sandbars, you would expect the highest concentration of the densest material, that would be things like gold. And then other material will be further away as the fluid velocities, the flow velocities decrease even further. So you tend to find a concentration of heavy minerals right on the edge of these gravel bars in such river systems. So this is the highest concentration of gold, is where you would expect to find in such a system. And then we can use something like Stokes' law in physics, which gives you the settling velocities of particles with different densities and different grain sizes. So we can use this equation of the velocity of settling is 2g r squared. G is gravitational attraction, universal gravitational attraction. G is Earth's gravity. Rho is the particle density, rho particle minus the density of the fluid over the 9 times the viscosity of the fluid. So when you do these calculations, and you can do that for water, you can do it for other things like air, you can see that to have the same settling velocity, which is what we call hydraulic equivalence, for a piece of quartz to be in hydraulic equivalence with pyrite, to be in hydraulic equivalence with gold, you need to have vastly different grain sizes because of the different densities of what we are talking about. So for quartz, you will have a much bigger quartz particle, a smaller pyrite grain, and the smallest gold grain, and they will be in hydraulic equivalence. They will be moved by the same velocity of flow of flowing water, and will settle at the same velocity. They'll be hydraulically equivalent. So if these minerals are hydraulically equivalent, you will expect to find them in the same rock that was deposited by water, but with these different grain sizes. And this is exactly what we find in the Witwatersrand reefs. When you look at the size of the quartz pebbles versus the size of the pyrites versus the size of the gold, they are all in hydraulic equivalence. And there have been experiments that have actually been done using sediment flumes, where they set up this in the 1980s at the Chamber of Mines Laboratory in Johannesburg to actually model the flow of gold particles and pyrite sand with flowing water. And they could show this experimentally as well. This is where you would expect to find gold concentrated on the edges of these bars where the flow velocity drops down, and what kind of grain sizes. Now let's go back to the gold reefs themselves and see where do you find the concentrations of gold. And here is one of these places. This is a channel within quartzites. It's filled with conglomerate pebbles, and when you look at the gold distribution along this gold reef, you see that there's higher grades on the flanks of the channel, exactly where theory would predict that you would expect to find the gold settling down first as water velocities decrease on the edge of a channel. So these kinds of processes of high gold grades right on the flanks of the channel are explained by a sedimentological model, and cannot be explained really by a hydrothermal model. The hydrothermal, if the gold was just coming in, it wouldn't care where the conglomerate was deposited. It would just depend on chemical conditions and so on. And they don't change that much. It was the flow velocities that changed on the sides of the channels, not the composition. So we can see a strong sedimentological control on the gold distribution in detail. And when you look at where the gold is situated, aside from gold, there is also other things like zircon concentrated together with pyrite, and there's chromite. And in fact, one of the other components very interestingly in the Wits Basin is diamonds. They have found the oldest diamonds in the world in the Witwatersrand gold reefs. They do not recover diamonds because everything is crushed to recover the gold. But in the old days, in the 1890s, they were hand-picking the ores. They could actually pick out diamonds. The biggest one found in the Wits reefs was 5 carats. And we still have a few samples left of these detrital diamonds, and they have some precious information about the conditions in the mantle if you study the mineral inclusions and so on. But this is the common heavy mineral suite that is found in the conglomerates. You find zircon, pyrite, chromite. You also find uraninite and things like monazite that you see here. Now, the zircons are important because they allow us to date the actual reefs themselves. So this was dating done by my colleague Lawrence Robb. I see he's due to give a course later on in the year. Back in the 1990s, he did a study of dating detrital zircons out of the Wits gold reefs. And we could compare the Wits gold reefs, which are the zircons from there, which are shown in red, compared with these are the Central Rand group. The Dominion group ones are shown in the blue colors, and from the Murchison Greenstone belt, you can see that some of the granitoids there are within the range exactly of these at about 3 billion years. So perhaps some of the greenstone belts to the north of the Wits Basin may be providing some of the material that you see in the reefs in terms of crustal formation ages. The other component in the Wits reefs is uraninite. And this is very interesting. The uraninite is nicely rounded, as you can see. There are also other grains which have different shapes, but there are some very clear rounded uraninite grains. And they are clearly of detrital origin, just like the pyrite. And it tells us also something about the surface conditions. That if you've got pyrite and uraninite stable in the surface environment, there cannot be any free oxygen in the atmosphere, because otherwise you will not get those as detrital minerals. So the detrital pyrites and the uranianites have been worked on and dated. The detrital pyrites give a couple of different ages. One group give ages of 3.134 million years, which is older than the Wits Basin. They clearly derived from an older, maybe an Archean greenstone belt kind of a source. But there are also some younger lead ages, which are clearly the ages of some later hydrothermal overprint or some recrystallization event in the pyrites. So where do all these things come from? Where could the components that you find in the reefs, the detrital zircons, the pyrites, and uranianite, and the gold, where could it come from? The easiest one to explain is the uranianite and the zircons, because they come from the surrounding granites. But the pyrites are a big problem. You have to find a source with big pyrites now, and then you've got things like these greenstone belts to the north, which are coeval with the Wits Basin. There's also greenstone belts to the west of the Wits Basin, which have been dated at about 2.9 billion years, the same sort of age as some of the lower Witwatersrand rocks. So we do have these younger greenstones that, if you interpret the greenstones in terms of some tectonic setting, there could have been a magmatic arc, and that could be then eroding to provide the detritus that you see in the Witwatersrand Basin. But if we want to account for the gold, we cannot appeal to this model to explain why there is so much gold. You can explain it if there was one conglomerate horizon at the base, like you find here, that has got some gold. But if you do a mass balance calculation, the amount of gold that is in the Wits Basin, 50,000, maybe 100,000 tons in total of gold, in order to produce that by erosion, you need to have all of that gold somehow exposed at the time that these sediments were being deposited. And if you think about the largest greenstone-hosted gold deposits in the world, like Barberton, the Sheba mine, or Kalgoorlie, you will need 20 Kalgoorlies, entire districts that are exposed at the same time to provide enough gold to account for the amount of gold you see in this basin. So that is one of the biggest problems. It's just the sheer amount of gold. You know, you can find plenty of greenstone belts, but you do not find in these greenstone belts any phenomenally rich amounts of gold. Now you can argue that maybe it's because it was already eroded, but we can't see a process that is different in these greenstone belts from anywhere else in the world. So that is one of the first order problems, is to account for the amount of gold. Even though the processes we can see are adequate in terms of sedimentological controls, the mass balance is a problem. If we look to the north of the Wits Basin, here are these Archean greenstone belts. They have the right sort of ages. So perhaps there was a big magmatic arc to the north and to the west as well. That was at least providing some of the material and perhaps some of the pyrite. You know, in the greenstone belts you do form massive sulfides, and perhaps some of the pyrite is coming from there. The pyrites also contain, there are also, aside from pyrite, there are small amounts of nickel and cobalt bearing sulfides as well that are rare, but they are present in the Wits reefs, and they are rounded as well. They appear to be detrital. There are also platinoids in the Wits reefs. They are platinum group elements. So that's coming from some ultramafic source. They could easily come from greenstone belts. The main problem is to account for the sheer amount of gold. So for that, we have the other hypothesis, the hydrothermal model, which has been going strong since at least the 1890s. And in the 1930s, there was a Harvard professor, Grattan, who came to South Africa, spent a few months there, and wrote a paper which was published by Economic Geology as a special monograph about the hydrothermal origin of Witwatersrand gold. And he wrote this huge monograph in a very didactic and polemic kind of way. That was more like a legal argument rather than based on evidence. And he stated in the next volume he's going to give all the evidence, but he never published the next volume, only this one. And for many, many years, South African geologists were convinced about the placer origin for Wits gold, because it explained most things, the sedimentological controls and all of that. But then there was a neo-hydrothermalist school of thought, which started with the arrival of Neil Phillips at my university back in the 1980s. And Neil Phillips is an Australian geologist. He's now very famous. He worked with David Groves a lot on the origin of Archean hydrothermal gold deposits in the greenstone belts. And he applied his mind to the problem of the Witwatersrand gold. Now, let's look at maybe some of the evidence that some of the gold is hydrothermal in origin. Well, here we see the Ventersdorp contact reef at one of the mines near Klerksdorp, which is overlain by lavas of the Ventersdorp supergroup. And when you look within this reef, you see lots of quartz veins cutting through. And the quartz veins do actually contain gold. And some of these veins actually cut into the overlying lavas. And they have nice hydrothermal gold in them. So the quartz veins indicate the passage of hot fluids and the precipitation of silica. The bulk of the veins that you actually do find are not mineralized, but you do find some mineralized veins. And the sort of the new hydrothermal model put forward by Russell Myers and Neil Phillips, all people that I actually worked with in the early 80s, is the following: that the reason why gold is confined to the conglomerates is due to porosity. The conglomerates are much more porous and permeable than the quartzites surrounding them. So if you have fluids moving through the basin, they will preferentially move through the conglomerates. That's point number one. Point number two is you have a lot of pyrite in the Witwatersrand reefs, as I've shown you. But there is almost no iron oxide. There is no magnetite in the Witwatersrand reefs. And yet, if you look at the source rocks, any of the granitoids surrounding the Wits Basin have got magnetite. And there is plenty of magnetite-bearing rocks in the surrounding areas. So if you had a normal kind of a sediment, it ought to be rich in heavy minerals that include magnetite. Magnetite is a component of black sands, heavy mineral layers in most sediments, but it's absent in the Witwatersrand reefs. So why? How is it possible to have the absence of magnetite? So according to this model, in fact, there used to be iron oxides present as detrital minerals, but they were replaced by pyrite. They were sulfidized at a later stage by hot hydrothermal fluids which came through the gold-bearing reefs and replaced iron oxide with iron sulfide. And there are examples that have been known, in fact, since the 1950s, when the famous German mineralogist Paul Ramdor actually studied the Witwatersrand basin and its reefs, and he showed that there are some detrital iron oxides that have been incompletely replaced by pyrite, but there's still some magnetite and ilmenite that is unreplaced in the core. So he showed that there are such textures going on of replacement. So this model, a hydrothermal replacement model, suggests that that is what has happened on a wholesale scale in this basin, where fluids have advanced through the basin and replaced iron oxides. There is also the evidence from the quartz veins for beautiful octahedral gold crystals like this, which have clearly crystallized out of a hydrothermal fluid. And of course, I've already told you, when you look at the typical gold grains, the very fine-grained gold, in any typical Wits gold reef, it looks like this. It's very irregular and crystalline, and very unlike placer gold, which would be rounded. And also, you get textures like this. You see pyrite grains which have been completely shattered, and then there's gold in between that's cementing the different fragments. So it's clear that there is some later event that has happened where the gold has been introduced and has cemented this rock. Now, some of this fracturing that you see here can be attributed to the effects of that huge Fridefort impact structure, which is 2 billion years old. It's the largest impact crater on Earth, 300 kilometers in diameter, and we would have mobilized a lot of hydrothermal fluids at a much later stage, and that could have done some of this that we see here. The other thing is textures like this one I showed you before, where you see veins of gold that are basically surrounding completely the detrital rounded grains of pyrite. But this is a vein, and it's clearly deposited by a solution rather than being composed of detrital gold particles. So all of these kinds of textures are what the hydrothermalists have said, this is the evidence for hydrothermal introduction of gold. And then you can see also later on the pyrite grains are recrystallized completely. So there is clearly another generation of pyrite which is crystalline and sometimes intergrown with gold. So these are all the kinds of features that have been associated with this hydrothermal model. And I showed you earlier the pyrophyllite alteration, and that plays an important part in the story of this wholesale introduction of hydrothermal fluids at the later stage that is also producing alteration. Pyrophyllite and chloritoid is another metamorphic mineral. So it's basically lowest Greensius facies sort of, conditions, maybe just reaching about 400 degrees centigrade. And under those conditions, you can mobilize a lot of gold as well. So Neil Phillips has come up with maybe the latest version of his hydrothermal model, tries to explain why there is so much gold. Because even if it was hydrothermal in origin, you still have to explain why there's so much gold compared to any other hydrothermal deposit on Earth. Because if there's 20 Kalgoorlies, and Kalgoorlie itself is formed by hydrothermal fluids, then Witwatersrand is 20 times bigger than the entire Kalgoorlie district. And there is no other known greenstone district in the world that is so big. So even the hydrothermal model, you need to come up with an explanation. So Neil Phillips teamed up with the metamorphic petrologist Chris Powell at the University of Melbourne, and about 2010 or so they published a paper in the Journal of Metamorphic Geology where they suggested a metamorphic dehydration model for the Witwatersrand Basin. That is the dehydration of the crust surrounding, and they simply took like 1 part per billion or something as the average gold content of that crust, and through some process of metamorphic dewatering, they could, but fluid focusing along these narrow channels. So a lot of metamorphic fluid with very low content of gold, but concentrated along very thin parts of the stratigraphy. So, and they accompanied by intense alteration and so on. And this is how they explain this huge volume of gold that has been introduced. But people have continued to study the Wits gold, and yes, you can look at euhedral pyrites like this, and some of them give much younger ages, 2.5 billion years, and so you can date some of the hydrothermal events and say, yes, there was a hydrothermal event at 2.5 associated with these euhedral pyrites. But it's not the end of the story, because you can date all of these things, but what about the gold itself? So there was a study done by Ruiz et al. At the University of Arizona, where they took individual gold particles and analyzed them for osmium. And using osmium isotopes, they were able to date the gold using rhenium-osmium dating. They dated individual gold particles, and both types, including the crystalline set of gold. But even if it's crystallized, it's not going to change its chemical composition if it's recrystallized. So they dated those gold particles, and the age they got for the gold itself was about 3.2 billion years, which is much older than the Witwatersrand Basin itself, and which sort of proves a detrital origin for the Wits gold. So they published that in Science and in GCA and so on. So the debate still continues. There's very good arguments from both sides. So the current sort of consensus, I would say, if you like, mainly based on the work of Minter and Hartwig Frimmel and Lawrence Robb, is a modified placer. That is, it originally started as a placer deposit, but then was modified by later hydrothermal events related to the history of the basin, so that accounts for the actual crystalline nature of the gold, accounts for some of the epigenetic veins and even the gold particles and the late crystalline pyrites. But it's also very clear that some of the pyrites and the uraninite and the gold was clearly of detrital origin. So it has a polyphase history. To what extent gold may have been introduced by hydrothermal activity is unclear. So people are still studying individual gold fields, and now they're looking at trace elements in the gold particles. And you find that it's actually different in different gold fields. If it was all hydrothermal and all introduced at once, it should be more or less the same. But you find big differences between individual alluvial fans and individual sources of entry, and they have different source regions, and the gold particles themselves have got different trace element chemistries. So it's again still supporting a modified placer model, but that model still cannot explain why there is so much gold. Maybe it's the sedimentological processes happening on the basin edge of reworking that makes it richer and richer and richer. But what is the role of organic matter? Why is there so much gold associated with carbon? Those are all questions that have not yet been answered, because it's like everything else about the Wits Basin. There are controversies. There are controversies about the origin of the carbon. Is it algal material? Is it hydrocarbons? Are the hydrocarbons indigenous to the Wits Basin, or do they come from the overlying Transvaal supergroup during diagenesis as some kind of a mobile petroleum? So there are all these kinds of questions that still have to be answered about the Wits Basin. Currently, there is a study going on with the University of Tasmania at Codes, together with the University of Johannesburg, which is the other university in Johannesburg. And what they are finding is that perhaps some of the gold is actually forming at the time of sedimentation. It's being trapped. Some of the pyrites may be forming like that. The people are studying the pyrite morphologies and finding that there are some very weird things going on with the pyrites. Some of the pyrite might actually be growing because it's framboidal in nature. There's framboidal pyrites in the Wits Basin which are too fragile to have been detrital. But they must have been growing in the sediment, and there is gold associated with that. So there are all kinds of questions about the role of microbes in maybe trapping some of the gold. We know today, for example, the Witwatersrand mine dumps are big sources of acid mine drainage because of all the pyrite there is in those deposits. And so there's a lot of very acidic mine waters coming out of the oxidation of the pyrites, sulfuric acid. And this is also rich in heavy metals, because aside from pyrite, there's cobalt, nickel, other metals, and uranium as well. So it's a toxic mess that's coming out, and it's going into the groundwaters. And to the south of Johannesburg, there are wetlands, there are swamps where there's a lot of biological activity, and they actually clean up all that water. The wetlands are helping to filter out all these all the metals and precipitating them. And one of my colleagues at my university in the chemistry department has been studying some of the algae and find that they are actually trapping gold. The algae are precipitating gold today out of those waters. So if this is happening now, it could have been happening in the Archean as well. So perhaps the role of biological activity is underrepresented in all these models, and perhaps it played a much bigger role. 40% of the Wits gold is associated with carbon, and maybe that carbon was biologically active and was actively precipitating gold at that time. Something else I discovered is that overlying the Witwatersrand basin in the east of Johannesburg, there are Karoo sediments, Mesozoic. And in the lower part of the Karoo, there are Permian coal seams in the Karoo beds. And some of those coal is lying directly on top of Witwatersrand reefs. And I found in a very old paper from the 1890s, a German professor took some of the coal and got the ash from the coal after you burn the coal, and he analyzed it for gold. It was running at about 30 grams per ton gold. So it's possible that maybe something similar was going on as well, that even during the Permian times, algal mats growing on top of gold-bearing sediments are trapping gold that is being released by weathering. So this may be one of the avenues of research in the future to look at the role of biological activity. There's been a lot of work done experimentally and in other fields, in microbiology, where microbes can actually trap gold or precipitate gold biologically. So this is probably the future directions in which the research is moving. But I have to end by quoting one of my old professors who died many years ago, Professor Desmond Pretorius, who was the founding director of my institute, the Economic Geology Research Institute at Wits University. And in the last public lecture that he gave in the 1980s, this is what he said about the Witwatersrand gold. He said, when the last ounce of gold has been mined out of the Witwatersrand basin, they will still be arguing about where the gold came from. Okay, so I'll leave it there. Thank you.
Thank you, Sharad. A gente está tendo problemas de recepção em Porto Velho, Belém e BH, relatados até agora. Eu não sei com relação às outras superintendências. Tem mais aí, né, Diana? Mas a gente vai continuar aqui e a gente tem um tempinho, pouco tempo, não muito, para alguma pergunta de alguém. A gente não está recebendo nenhuma pergunta de fora, ou seja, das outras superintendências. Talvez alguém aqui tenha alguma questão. Eu acho, por exemplo, que a origem hidrotermal tem um problema grande com relação ao carbono, né? Quer dizer, como é que você imagina o ouro tão associado com carbono e uma origem hidrotermal para o ouro? Teria que explicar também a origem para o carbono, né? O que não é muito, que para mim não é muito fácil imaginar, né? I have a problem with the hydrothermal origin, which is the carbon. It's difficult to reconcile the origin of the gold as being hydrothermal with a, let's say, cogenetic origin for carbon as well. So I can't, because they are so associated, so related in the field. So it's quite a problem in my point of view. I don't know if you want to comment this.
Yeah. I think the hydrothermalists would say that the some of the carbon might be of mobile hydrocarbon origin. There are people who have suggested that, John Parnell, for example, and others would suggest that the gold is trapped chemically by the carbon, by reduction. So there could have been of any origin. It could have been biological or organic in origin, but the gold is actually chemically trapped by the carbon.
E há alguma possibilidade do processo hidrotermal ter antecedido o processo de place? Is there any possibility? And understand you mentioned something about the ages, but is there any possibility of the hydrothermal process have preceded the placer process and not the other way around? I mean, first hydrothermal, no, ages can't support that.
Well, you could have had a hydrothermal origin of the gold, but it couldn't have been in the Witwatersrand basin then. It has to be somewhere else if you had to precede the placer. I mean, it's obvious the placer model relies on gold being present somewhere else, and whatever the origin, it's hydrothermal or exhalative or whatever, but it has to then come in as a detrital component into the basin and then modified by later events, metamorphic events or whatever, to produce the recrystallization and the alteration and so on.
A minha pergunta é se a atividade hidrotermal, o registro da atividade hidrotermal é em locais muito específicos na bacia ou se é uma coisa mais distribuída pela bacia como um todo.
So hydrothermal is localized, what it's generally distributed in the basin.
There was a study that was published in Nature by a group from Leeds University many years ago, based on a lot of drilling through the whole basin, and they could see the entire package of conglomerates with lots of hydrothermal alteration on a basin-wide scale. They could follow this for kilometers, alteration assemblages associated with the reef packages. So they suppose that the fluids are moving mainly in the reefs and causing alteration around them.
E não é localizado, existem trabalhos de sondagem que mostram que esses fluidos percolaram toda a bacia, principalmente ao longo desses planos de acamamento dentro dos depósitos de placer. Mais uma última.
Eu queria saber como é que se tem alguma relação mais direta dessa cratera de impacto aqui de Vredefort com alguma estruturação ou mineralização no depósito.
Is there any genetic relationship between the crater structure with the mineralization of gold and uranium in the basin?
Well, we think that perhaps some of the textures that I showed, like the brecciated pyrites, they could be the result of this impact. There is also, in fact, breccias within the gold reefs and xerotachylites, sort of glassy sort of rocks, which are found in the Witwatersrand reefs. So there must have been some really massive shocks going through that basin as a result of this very large impact. And it must have generated a lot of hydrothermal activity. But the placerists would say this is one of the things that produced the hydrothermal overprint. Even the hydrothermalists are not saying that this is the reason why hydrothermal fluids are coming in, because it wouldn't explain where the gold actually came from. In fact, when you look at the dating of the pyrites, the secondary pyrites, they're around 2.5 billion years. Some of them are, 2.7. They are related to much older events than the impact, which is at 2 billion years. So there are a lot of other hydrothermal events that precede the impact. That may be one of the last major events of remobilization. So there may be even several such events in the history of the basin.
Bom, apesar de poder haver uma relação, principalmente com o impacto associado ao início dos processos hidrotermais, por questões, né, de idade, geocronologia, ele acha que alguns estudos, né, têm mostrado que pode ter havido mais do que um evento hidrotermal associado à mineralização. E também tem evidências, né, com relação do impacto, né, uma possível associação do impacto com a mineralização pelas texturas brechadas de alguns minérios que são encontrados na bacia. Ok? Bom, então a gente vai prosseguir agora. Houve uma pequena modificação, vocês devem ter percebido. O que estava como Lecture 7 no programa inicial, na verdade, o professor acabou juntando a Lecture 6. Então a gente agora vai, na verdade, para Lecture 7, o que no programa inicial estava como Lecture 8. Então não se perdeu conteúdo, mas houve um rearranjo da estrutura das aulas, ok? Então essa última parte que nós tivemos agora de tarde seria a Lecture 7, ela passou a ser incluída na Lecture 6 e agora a gente vai para a Lecture 8, ok? Thank you. All right, okay. All right, okay. Is it in the flash list? Want to try this one here? Stop here. Down there. 8. Yeah, son. Oh yes, it's not a PPT. Senta aqui. Ainda estão operando, mas no tipo abre, fica um tempo, depois fecha e continua. Is there any other sort of mineralization associated with the asbestos which are still under production in those mines? Maybe some sort of mine ore associated with ultramafic rocks?
Yes, there is in one of those complexes that I mentioned. There is talc. It is a mine that is dedicated for production of talc only. But talc is a very specialized product. You know, there's no big market for it, but it's used in the pharmaceutical industry and for, you know, facial powders and stuff like that. And so they are mining that for talc. In that same mine, you find some asbestos, but you also can find nickel sulfides. Okay. And there is adjacent to that talc mine, there is a prospect for nickel. This is in Barberton. Yeah, yeah.
Apesar das minas estarem fechadas em Barberton para asbestos, elas ainda funcionam para talco, né? E também tem sulfetos de cobre e níquel que estão sendo explorados. Ok. Então acho que a gente, não havendo mais questões, a gente passa então para Lecture 8. We're now okay with the time because it's 3:15. So don't have to rush. If you want to go into more detail, it's going to be okay. Okay. Thank you.
All right. Okay, so now we will move on to the subject of chrome and PGE inlaid intrusions, but still dealing with Archean rocks. And the best example that we have of an Archean layered intrusion with chrome and platinum group mineralization is the Great Dyke of Zimbabwe. So the Great Dyke is in fact not a simple dike. It's in fact a layered intrusion. It's a mafic, ultramafic complex, and it is up to 8 kilometers wide and 550 kilometers long. So it's one of the largest intrusions of its type in the world, second largest layered complex after the Bushveld complex in South Africa. And it has been now very well dated at 2580 million years. So it's neo-Archean. Previously, when you had the rubidium strontium ages, it was thought to be about 2.4 something. Now we have a good date of 2580 million years, which means that it's only 20 million years younger than the major granitic event that stabilized the Zimbabwe craton. The big event of potassic granites at the end of the greenstone evolution in Zimbabwe was 2.6. And this is at 2580 million years, 2.58 billion years, just 20 million years later. The Great Dyke is made up of ultramafic rocks and cumulates and gabbros. It's got dunites, hartsbergites, and gabbros. It's got many chromitite seams, and it has a platinum group bearing main sulfide zone within a pyroxenite, which is the second largest platinum group element resource in the world after the Bushveld complex. So it's of very great economic importance to the economy of Zimbabwe and in terms of platinum sources. So it cuts right across the entire craton, cutting across the layered complexes. And so it is quite clear that it postdates the actual formation of the Zimbabwe craton, because it's actually forming in brittle fractures that cut across all of those greenstones and the surrounding granitic intrusions. So there must have been some big event on the craton which formed these fractures, because there's not just the fractures associated with the Great Dyke, there's a whole set of these fractures parallel to that which cuts across the entire craton. Here is the cover of a book that was published by the Institution of Mining and Metallurgy in London, based on a conference volume. There was the 5th Magmatic Sulfides conference that was held in Zimbabwe in 1987, and this is the conference proceedings of that. There are lots of papers dealing with the Great Dyke and its magmatic sulfides. So this is one of the best sources of information that we have about the Great Dyke. And in this volume there is a paper by Wilson and Prendergast where they came up with a model to explain the fracturing of the Zimbabwe craton. They suggested there were events in the Limpopo belt which produced a set of conjugate fractures that you can see like this, including the one that is occupied by the Great Dyke, but that was due to a stress field that was northwest, southeast in this direction. But then at the later stage, the stress field changed to what you see here, and then produced tensional opening up of these fractures that were previously formed as conjugate fractures, and allowed for the intrusion of the Great Dyke. Now notice, of course, the ages given here are 2460 million years, but we now know that the Great Dyke is 2580. So it's 120 million years earlier than what's shown in this paper. And then subsequent to that, the stress field changed again and allowed the Great Dyke to be broken up again by more brittle faults. Here's another model, this time from Paul Dirks, which shows the fracturing of the Zimbabwe craton, and perhaps relating to some kind of a stress field in this direction, perhaps related to oblique subduction along the western boundary of the Zimbabwe craton, and some kind of extension producing this set of fractures. Now the Great Dyke was mapped at a 1 in 100,000 scale by one man who spent 6 years of his life in the late 1950s, from about 1954 to 1959. Ben Worst, who died about 3 or 4 years ago, he walked the entire length of the Great Dyke, and he published this very famous set of maps that were 9 maps, 1 in 100,000 scale, to cover the whole Great Dyke. And at the 100,000 scale, it will occupy about the size of this wall. So it's a very a fantastic set of maps. It's out of print, but you can get it electronically. But a wonderful set of maps where he differentiated all the different rock types, and they stand out very clearly on aerial photographs. If I just go back to this slide, you can see an aerial photograph here, and you can see the layering very, very clearly. So it's not difficult to produce a map as detailed as this one here. But he also accompanied that with lots of cross sections. You know, every few kilometers there were cross sections across the Great Dyke, and a continuous longitudinal section as well. So these are just 3 out of the 9 or 11 maps that constitute his great piece of work. And this was published in 1960. Subsequent to that, most of the research work on the Great Dyke has been done by Alan Wilson, who is one of my colleagues at Wits University. He retired about 2 years ago, but he's still running the laboratory there. And he has spent 4 decades of his life working and doing research on the Great Dyke and on its layering and so on. So he's published a lot, and I've been fortunate enough, again, to be able to accompany somebody like this with his wealth of experience to the field to look at the Great Dyke. And here we are in the very center of the northern lobe of the Great Dyke. It's got 4 sort of centers that are boat-shaped, and on one of them you can see the actual layering. So if you notice here, this is the northern part of one of these lobes, and the layering is actually dipping shallowly inwards. Here's the cross section, and here we can see on the photograph the layering dipping in like this, and the layering dipping in that way, and in the middle it's flat. So this is the actual outcrop of the layered mafic ultramafic succession. And within this layered complex, if you look at the lower part of it, it's the lower ultramafic sequence, which has got dunites at the very base and pyroxenites or bronzitites above that. And at the very top, you have a mafic sequence with gabbros. Now, the gabbros are only found in 4 separate places. Right down at the bottom here, this dark gray unit is where you find the gabbros. The rest of the complex consists just of the dunites and the pyroxenites. That's what it is. So in the layered succession, the most of what is outcropping is this lower part, the ultramafic sequence, with dunites at the bottom and a series of layered bronzitites or pyroxenites over here. There's a number of cyclic units within this. Now, of great economic importance, within the lower ultramafic succession, in the dunites, you have a number of thin chromite seams. So the chrome that's shown here, the chromatites, they can vary from just a couple of centimeters in thickness to the maximum of perhaps about just over a meter in thickness. And these are very high-grade chromatites. They are even better than the ones in the Bushveld complex in terms of the chrome to iron ratios. And they have been mined in a number of deposits. And there's a lot of artisanal mining still going on, because there's also a lot of alluvial chromite that's being washed by the rivers into rivers and being mined by artisanals. But of the greatest economic importance in the Great Dyke is that right at the top of the pyroxenite succession, just below the contact with the gabbroic rocks, there is a pyroxenite which is rich in platinum group mineralization. And this is called the main sulfide zone, because it contains nickel iron sulfides as well as PGEs. So that is what is being mined everywhere where their mines have been established in the Great Dyke. So let's look at some photographs. Here we see some old workings for chromatites. They've been trenching right along the outcrop of the chromite seam, and these are dumps coming out of the mines, showing the chromite, where the chromite workings are in the lower ultramafic unit, which is now serpentinite. And overlying the serpentinites in the background, you see the more forested pyroxenites. Here is another picture taken showing you 2 chromite seams in outcrop, with the trenching and the workings that have been going on right along that contact on outcrop, with the workings associated with the mining of the chromite. Here is one of the chromite seams in outcrop, very thin. It's only a few centimeters in thickness, and this is the kind of stuff that was being mined. So these are massive chromatites, and the serpentinite above is very rich in chrome with a sort of a net texture. Here is a lump of high-grade chromite ore, which is got a very high chrome to iron ratio. It's what they call metallurgical grade chromite, and chemical grade chromite. So here there is the national road in Zimbabwe going west from Harare, and as you approach the Great Dyke, you can see that the first rocks that are outcropping have got very little vegetation on them, because these are the serpentinites after dunite. In the background, with the more vegetation, are the pyroxenites, which have got more fertile soils. In the foreground, it's not a lack of fertility, it's actually the fact that the soils are poisonous to most plants because they are very rich in nickel. The nickel is in olivine. When the olivine gets serpentinized, that nickel gets freed, and then it's an environmental poison. These are high metal soils, and very few plants can tolerate these high nickel soils. So there's only very specialized plants that can grow there. The average trees cannot grow on the soil, and that produces the big contrasts in vegetation, which you can see on the aerial photographs and the satellite images of the Great Dyke. It helps greatly in the mapping. So here we see the Great Dyke Pass, and you're going past some outcrops of serpentinite. And there are some good exposures along this pass. Here we see a pyroxenite, which is weathered, but you can also see some nice fresh exposures of the pyroxenite, showing very coarse grain size, accumulate textures. They are clearly formed by some process of layering, of accumulation in a magma chamber. So this is a layered mafic, ultramafic sort of complex. Now the platinum industry in Zimbabwe is fairly young. In South Africa, platinum was discovered in the 1920s in the Bushveld complex, and there's been continuous mining for almost 100 years of platinum in South Africa. In Zimbabwe, platinum was actually also discovered in the 1920s, and for a short while there were two brothers who established a small little mine where they did a little bit of chromite mining for a few years in the 20s. But since that time there was no further mining because of the much richer and much better platinum mines that were developed in South Africa. But in the 1980s there was a resurgence in interest in the platinum, and from the 1990s onwards they started reopening this new era of platinum mining in Zimbabwe. So it's a relatively young industry, but the platinum mines are some of the most important sector in the mining industry now in Zimbabwe. It rivals gold in terms of revenue being generated from the mining industry. So there are a number of platinum mines. The first one to start up in the 1990s was this mine, the Hartley Platinum Mine here on the western side of the Great Dyke in the north. And in this deposit, you can see at the lower ultramafic part, you find a lot of cyclic units going from bronzite from bronzites and Hartsbergites. Then there is a big, thick pyroxenite unit, a bronzitite over here, and then there is a Websterite up in the north, just before you get to the Gabbro. And over here in red is this bronzitite, a pyroxenite unit, which is the main sulfide zone. This is where the platinum mineralization is found in the Great Dyke, in this particular horizon. Now, you saw the mapping by Ben Worst of the Great Dyke and his cross sections. His cross sections were very idealized because he had no subsurface information. So he drew his cross sections in this sort of way. But subsequent to that, there was a major gravity study done, a geophysical study done of the Great Dyke and its layering by people at the University of Zimbabwe. And on the basis of interpreting the gravity, this new profile was sort of established, and also on the basis of drilling information that we had later on. So it is more of a champagne glass of funnel sort of shape compared to this rounded shape that Ben Worst had. And it's going to be open at depth because it's a dike-like feature which is continuous for 500 kilometers. But somehow the magma got ponded and was layered to produce this kind of layered sequence dipping in towards the middle. Very unusual kind of feature. Now, here is an outcrop of the main sulfide zone of the Great Dyke, which shows you this very coarse-grained bronzitite pyroxenite, and it's got a very red, intense color from the oxidation of the sulfides that are present within this unit. When you look at the fresh main sulfide zone under a microscope, you can see a whole range of different platinum group minerals associated with base metal sulfides. So they're associated with pyrite, pyrrhotite, pentlandite, chalcopyrite, and so on. So here you can see pyrite, chalcopyrite, pentlandite, and pyrrhotite. And in the oxidation zone, in the near surface, there have been a lot of changes in the mineralogy from the oxidation of these primary platinum-bearing sulfide phases, platinum group elements, platinum group minerals, and a very detailed study has been done of the oxide mineralogy and published by Lockmellis et al. In 2010. What they've shown is also the comparison of the values within the main sulfide zone in the oxidized ore versus the more pristine ore. And there's been some mobility of platinum and palladium and gold within this environment. But the grades, the average grades are running at probably about 6 parts per million in the richer parts of this main sulfide zone. Now, the mine that Hartley Platinum was started by BHP in the early 1990s, and they started with mining in the oxide zone and a big open pit mine that was started on the outcrop of that main sulfide zone. And subsequently, they've gone underground. So most of the current operations are underground, following the main sulfide zone, but it initially started off in this very oxide-rich pit. But when they went underground, and I'm talking about BHP now, they ran into a great deal of trouble. The first problem with BHP being a very huge mining company, and they were based at that time in San Francisco, and they were running the operations out of San Francisco office to try to run a mine in Zimbabwe. It doesn't work. You cannot run a mine by remote control. You have to be on the ground and solving problems on the ground. So the first problem they ran into was that their ore body model was wrong, because it was based on drilling and just interpolating between drill holes. But what they did not take into account when they developed along the ore body, and they discovered that there's lots of minor faulting, just small little faults that displace the ore body by 0.5 meter, 1 meter. But it's sufficient to completely destroy your mining methods, because that amount of displacement, when the ore body itself is about 2 meters, a 1 meter displacement is 50%. And that means that they were planning to just mine with mechanized mining, nice linear stopes. But when the ore body is chopped up into little small pieces, it has to be controlled at a much greater level and be mined in a more flexible way. And they basically gave up and they pulled out of Zimbabwe because they weren't able to make any money out of it. But the other companies took over and are running it like a small mine rather than a big mine, and are able to continue mining. So there are South African mining companies with a lot of experience mining in the Bushveld complex. There are some of the major players now in the Zimbabwean platinum market. Impala Plats, Implats, and Zimplats, for example, are some of the big companies operating in Zimbabwe. So Zimbabwe is the number 2 platinum producer in the world after South Africa, after the Bushveld complex. And if you've been following the news since about 2012, when about 38 miners were killed in a strike at one of the platinum mines, the platinum mining industry in South Africa has been in a turmoil for the last 2 years. It's been a lot of strikes. They're still on strike as far as I know. Last week they went on strike, and I don't know whether it's been resolved or not. So there are major political problems, labor problems in the South African platinum mines. But South Africa produces 80% of the world's platinum. And so somehow if there's any problems in platinum mines and the mines close down, the platinum price goes up. And so the South African mines will always continue even with all their problems, because they control so much of the platinum production. But the importance of Zimbabwe is that if there is a company or a country that relies on a reliable source of platinum, then they want to diversify where they get the platinum from. So you don't want to rely on one producing country, because if that country goes up in flames, then you're going to lose your market, your source of platinum. And platinum, as you know, is mainly used in catalytic converters for green cars. There's also a significant part of the platinum market now, about maybe 20%, which is now used for jewelry. And mainly in the Far East, in China, Japan, and places like that, where, and even now increasingly in India, they are even marketing platinum as jewelry. It's never been like that traditionally, and nobody else would buy. I wouldn't buy platinum jewelry because it looks just like stainless steel. So we don't know the difference. But it is being marketed for jewelry purposes. But it all depends on whether, and somebody doesn't find an alternative to platinum to use in catalytic converters. It could destroy the platinum market completely if any chemical substitute was found for the use that it's used in exhaust fumes in catalytic converters. Okay, so that was a great dike.
Is that the last lecture for today, or we start with, I think, lecture 10?
Yeah, we still have
Então tá, pessoal, olha só. Então a gente ainda tem mais uma lecture para ir, que é a 9. Ok? Nós estamos na 8. É porque teve uma pequena reestruturação do programa, né? Então nós estamos na 8. Ele acabou de apresentar a 8. E nós vamos passar para a 9, que a gente já vai entrar no paleoproterozoico. Então, isso. Obrigado. Então a gente... são 20 para as 4. 4 horas a gente vai parar para o coffee break. Ok? Então a gente tem um tempo bom aqui para perguntas sobre essa última aula. Eu continuo não recebendo nenhuma dúvida do pessoal de fora, a não ser reclamações. Então a gente tem um tempo aqui, talvez 15, 20 minutos até o coffee break. 15 minutos coffee break, daqui a 15 minutos. Então beleza. Então a gente tem 10 a 15 minutinhos para perguntas, se alguém quiser, por favor. Francisco.
Eu queria saber se existe alguma diferença significativa entre o Merensky Reef e o Main Sulfide Zone. I would like to know if there is any significant difference between the Merensky Reef and the Main Sulfide Zone.
There is a very big difference between the main sulfide zone and the Merensky Reef, and that is in being able to recognize the main sulfide zone. The main sulfide zone is just a it's a bronzitite pyroxenite, but it's surrounded by pyroxenites and websterites which look very similar. Whereas in the Merensky Reef, firstly, it's a very coarse pegmatoidal pyroxenite, very different in grain size. Plus, at the bottom and the top of the Merensky Reef, you have a thin chromite seam. And sometimes the footwall is anorthosite or some mottled anorthosite or something like that. Very, very different lithology. So even a miner, never mind a mining engineer, even a miner can see the difference between the Merensky Reef and the rocks either side of it. Whereas even a geologist will find it very difficult to tell the difference between the main sulfide zone and the rocks on either side. So it's a big problem. The problem is that when there is a minor faulting and it's moved a little bit, you could have moved out of the mineralized zone because the it's also not very visually, it doesn't stand out visually, so it's difficult to judge unless you've got some way of, you have sampled it and you know that this is the top and the bottom in terms of the sulfide values, and then only you can sort of judge where to mine. So that's one of the big problems in the main sulfide zone. That is, in fact, why it wasn't really mined for all these years before the 1990s, because people just couldn't actually make the connections, in different drill core and so on. It doesn't stand out like the Marinsky Reef. Marinsky is very easy.
Então, basicamente, a diferença fundamental entre Marinsky e o Grande Dique é que em Marinsky as litologias são tão contrastantes que fica muito fácil visualizar a mineralização, enquanto que no Grande Dique, no Great Dyke, elas não são tão bem visualizadas porque as litologias que estão acima e circundando as camadas mineralizadas não são muito fáceis de distinguir em termos de litologia e cores. Por exemplo, lá em Marinsky você tem camadas de anortosito, enquanto que aqui são camadas de piroxenito com outras rochas ultramáficas, né? E também tem a questão do offset, né? Por causa das falhas que deslocaram essas camadas mineralizadas no Grande Dique, né? Então, basicamente a diferença seria essa aí. Ele até disse que no caso de Marinsky um mineiro consegue visualizar facilmente a camada, enquanto que um geólogo mesmo teria muita dificuldade de visualizá-las no caso do Grande Dique, até mesmo porque mesmo com as sondagens, né, é difícil correlacionar as camadas mineralizadas por causa desses offsets, das pequenas falhas que afetaram as camadas posteriormente à formação delas. Ok? Se quer completar alguma coisa, tá tranquilo? É isso mesmo? Mais alguma pergunta? Well, do you have any information about the chemistry of the gabbro in the Great Dyke? Is it tholeiitic or is it alkaline? What sort of chemical composition? But I would expect it to be tholeiitic because it's quite usual for the tholeiitic magmas to produce these sheets of by accumulation. But I'm not sure if you have any information about that. Estou perguntando se tem alguma informação sobre a composição química do gabbro, que seria o magma parental, vamos dizer assim, que teria originado todas essas camadas de acumulados dentro do Grande Dique, se é toleítico ou calciocalino.
Okay, yes, I think there are tholeiitic gabbros. Also associated with the Great Dyke, there are parallel dikes. There's along the entire length of the Great Dyke, there are two dikes on either side, which are for the entire length of it. The one is called the East Dyke, and the other one the Umvumila Dyke, and they have a composition of quartz-rich gabbro. Quartz-rich gabbro, yeah.
So they would be tholeiitic.
Yeah.
Existem diques secundários associados ao Grande Dique que eles formam gabbros com quartzo, né? Então, bom, para mim isso significa que eles devem ser toleíticos, devem ser magmas toleíticos, quartzos toleíticos provavelmente, né? A gente tem uma pergunta então aqui de fora do Maicon. Perdão, é do Evilard, é isso? De onde ele é? De Teresina. A pergunta é qual... É isso mesmo, Teresina? Qual o controle da mineralização dos PGEs do Great Dyke? So we have a question from Teresina, finally, which is which control for the PGE mineralizations in the Great Dyke, the platinum group?
I don't know the answer to that question. But I think if I look at the models that have been proposed for the bushveld, it's due to magma mixing. There are more primitive magma mixing with a more evolved magma, and differences in sulfur saturation due to that. So in the Great Dyke, the sulfide horizon is very near the top of the gabbros, just before the near the top of the pyroxenites, just and below the gabbros, and that's the sort of stratigraphic position that you find it, and it may be related to a new intrusion that's related to the gabbros, and perhaps a mixing zone between the two sort of bodies of magma.
Which is more or less the model
for the bushveld as well, yeah.
Okay. Então o modelo possivelmente ele não gostaria de não ter que responder essa pergunta, mas o modelo é possivelmente similar ao modelo de bushveld e envolve mistura de magmas, né? Então os magmas essa mistura de magma acabaria levando a algum tipo de supersaturação em enxofre, que estaria relacionado então à mineralização no Great Dyke. Espero que a gente tenha conseguido responder a pergunta do colega ou da colega, o colega, desculpa, lá de Teresina. Estou sem óculos, viu? Então, ok, mais alguma? Dayana, fica de olho aí, por favor. Se aparecer mais alguma coisa, você avisa pra gente. A gente ainda tem mais uns 5 a 6 minutinhos. Se alguém tiver mais alguma pergunta, é só... Beleza. Se mandar, fala. Vou esperar, aguardar um pouquinho para a gente privilegiar os colegas que estão escutando a gente nas outras superintendências. Ok, estou chegando lá. Ah, tá. Fala. Um diápilo. Ah, de um arco. Então a pergunta do Francisco Vilela, de BH, não ficou claro, ele não conseguiu entender claramente a forma do dique, se é uma forma parecendo uma taça ou um arco. Ok. Okay, we have a question from Belo Horizonte, and he's asking you, it was not very clear for him about the shape of the intrusion. So is that more like a sort of a pipe shape, or is more like these layers, like an arc? It's not very clear for him.
According to some models, you have these 4 sort of areas where I show the gabbros. That's at the very top of the layered sequence in each of those 4 different complexes, if you like. There are 4. The Great Dyke is divided into these 4 complexes, each one ending up with gabbro at the top in the layered sequence. And each complex is in the form of a boat, like a closed ring, which is dipping inwards, not only from the sides to the middle, but from the top and the bottom, from the north and the south, dipping towards the center, the central part. So it's like a very elongate funnel that ends up into something that's shaped like a boat, and there are 4 of them stacked on top of each other along this big fracture.
So it's like having a big fracture,
yeah.
like a root. And
Yes. Yeah. Yeah. That's right. Yeah.
Bom, basicamente a forma a gente consegue eles conseguem dividir o grande dique em 4 seções distintas. Essas seções e profundidades adquirem a forma de um funil e estão conectadas a uma parte mais profunda que preenche toda a fratura. Então é como se você tivesse a intrusão tabular, e dessa intrusão tabular, então, essas 4 intrusões mais afuniladas acabariam dando a forma geral do dique. Eu espero que isso também tenha conseguido responder a pergunta do colega de BH. Tem mais alguma? Daiana, você consegue ver mais alguma? Então tá bom. Então vamos esperar, porque tem um delay. Quando o pessoal consegue receber, está tendo um atrasozinho na recepção. Vamos esperar um pouquinho mais, é isso? Só mais um pouquinho? Para ver se tem alguma outra pergunta de algum colega de fora. Nesse tempo, é claro, se vocês tiverem alguma pergunta, por favor, fiquem à vontade. Eu vou fazer uma perguntinha enquanto isso, até ver se tem alguma pergunta de fora. Eu achei interessante o modelo estrutural que ele apresentou aqui. Para a colocação do dique. Aqui deixa eu voltar aqui no modelo estrutural. Só um minuto. Por enquanto nada. Ok, vou fazer só uma última pergunta que está relacionada a uma rotação que levou à extensão. A colocação do dique está associada a uma rotação que com máximo estresse compressivo que causa extensão. E é por causa dessa extensão que o dique basicamente consegue espaço para intrudir, né? Eu queria saber se essa rotação com esse estresse compressional, se ele foi sentido nas encaixantes do dique, qual seria a origem desse, porque a gente já estava num estágio de cratonização quando o dique intrudiu. So I have a question. I can see here that the intrusion followed some sort of rotation after a great compressive stress, and the dike took this let's say discontinuity to intrude. And so my question is that possible to see the consequences of this rotation in the country rocks, and then and also as we were in a sort of cratonization stage, what would cause this rotation? I mean, in a craton, or I would expect it to be more tensional and not associated with that compressional stress, and it's possibly associated with strike slip sort of movement that would open a space for the intrusion. So can you see these in the country rocks, and it's related to which sort of let's say tectonic process?
Well, I think the first collision, according to Wilson and Prendergast, was in the Limpopo belt to the south, which has traditionally been regarded as a collision between the Zimbabwe and the Kappa Craton. All right, so if that collision, but the problem, as I pointed out yesterday, is that this was the same model, or even this morning, the same model used to suggest the Witwatersrand Basin was a result of the same collision, right? But the Witwatersrand Basin was formed at 2.9, 2.8 billion years, but the Zimbabwe craton was only cratonized at 2.6. So, which means that whatever produced the collision was younger and not related to something in the Kappa craton. Now, but we do have a Limpopo belt to the south of the Zimbabwe craton, and the Limpopo terrains are high-grade metamorphic rocks. They are granulites. They have been thrust onto the craton, and they are cut by the southern end of the Great Dyke, which means that they were there and placed before, and maybe that's what caused the fracturing, and then the intrusion actually stitched the craton and the mobile belt together at 2.58. But the craton itself only formed at 2.6 billion years. So that collision must have happened somewhere in that 20 million years between the cratonization of the craton at 2.6 and the collision with the north marginal zone of the Limpopo belt, and then intrusion by the Great Dyke at 2580. But there is also, in the north of the craton, another mobile belt, which was recently recognized only maybe about 10 years ago. Some mapping that was done and geochronology that was done by people in Zimbabwe and in South Africa, Hilke Jelsma, and found what he calls the Pfungwe orogenic belt. Now, it was in the very north of the Great Dyke. It's actually folded, right? And that folding is Pan-African in age. It's much younger, right? And the northern greenstone belts as well have also been deformed. And people always assume that this was a later event, which was, very much late Neoproterozoic. What the geochronology found in this study is that there is a collision event that predates the Great Dyke, because it's a high-grade metamorphic event which you do not see in the Great Dyke, which is surrounded by these gneisses. So this event also marks a post-cratonization event, a collision in the north, subsequently intruded by the Great Dyke. So we have a number of events that could be responsible for producing the fractures and maybe even for the rotation of the stress field.
Bom, então, para tornar uma resposta longa um pouco mais curta, né, basicamente existem algumas evidências de que muito próximo do período de cratonização houve algum tipo de colisão. Há evidência para colisão porque tem o Limpopo Belt ao sul e tem um outro tipo de orógeno no cinturão, né, um orógeno colisional mais a norte também, que só tem sido estudado mais recentemente, há cerca de 10 anos. E lá no norte, por exemplo, eles descobriram que existem evidências, apesar de ser um cinturão do Neoproterozoico, existem evidências para processos associados a hidrotermalismo mais antigos. Então ele acha que bem próximo do período de cratonização, né, basicamente a 2.6 e aproximadamente a 2.58, que foi o tempo de intrusão do Great Dyke, né, essas colisões poderiam ter provocado essa rotação e, portanto, com um stress compressional grande, a extensão por onde teria intrudido o dique. Bom, acho que agora a gente... tem mais uma pergunta de... E essa pergunta vem de? Então nós temos uma pergunta de Francisco da Sureg de São Paulo, que ele quer saber a que profundidade atinge a intrusão, não é isso? Hein, Diana? A que profundidade? So I have a question from São Paulo, colleague Francisco, and he would like to know how deep is the intrusion.
Well, back in the 1960s, there was a hole that was drilled straight down the middle of the Great Dyke, and it was, I think it was probably about more than 2 kilometers, and it was still in the layered sequence, which you could follow on the margins. So it's very continuous, the layering. From the geophysical modeling, they cannot, it looks like a dike feature even between the so-called complexes. You can still see that there is, it goes quite deep and as far as the modeling can allow. So it's not a shallow feature, there's no bottom that they can see. It must continue down as some kind of a dike.
2 kilometers at the
Minimum, yeah.
Então tem um furo, né, que chegou a atingir 2 quilômetros. Existem evidências geofísicas que pode ser mais profundo que isso, mas basicamente no mínimo 2 quilômetros de profundidade. Ok? Então agora a gente vai encerrar por coffee break e a gente volta daqui a 15 minutos para a próxima aula com o professor Char.
Basically going from a shallow water platform in which the stromatolitic carbonates are found to deeper water facies, and in that transition is where the iron ore deposits are found overlying the carbonate platform. So when you look at the carbonates, they have these beautiful algal stromatolites, and that is evidence for lots and lots of algal activity and photosynthesis. This is important, and it plays an important role in understanding the origin of the iron formations as well. So we can see the Shark Bay today in this hypersaline environment, and presumably the Transvaal supergroup also looked like this at some point with lots of stromatolitic carbonates forming those dolomites. So when we look at iron formations in general, we have these 3 types of iron formations. There's other types, of course, which are the oolitic iron formations that are found in the Phanerozoic. But when you look at Precambrian ones, we have these algoma types, which are the ones you find in greenstone belts, like the ones I showed from the Swaziland supergroup. And these ones are also the main source of iron in the greenstone belts in places like Zimbabwe. And they are associated with these kinds of exhalative environments, perhaps in a magmatic arc environment or back arc sort of environment where you've got hydrothermal activity and black smokers and so on. The much larger and more extensive Lake Superior type of iron formations are the ones that you find in the Transvaal supergroup and in the Hamersley Basin in Australia and also here in Brazil. And these are much more extensive, covering large carbonate platforms extending for hundreds of kilometers, and must be formed from the ocean through large-scale processes going on in the oceans, not through localized hydrothermal activity. And then the final type in the Precambrian is the Rapitan type of iron formations, which are associated with Neoporozoic glaciations, and they can vary quite a lot in thickness, from very, very thin horizons to things that are hundreds of meters in thickness, and they can also have associated manganese deposits like you have here at Urucum in Brazil. So banded iron formation is really a well-bedded chemical sediment that comprises alternating layers that are rich in iron and in silica. So the iron is usually in the form of either magnetite or hematite, and the silica is usually amorphous chert, or it may also have iron oxides intergrown with it, and it's red in color. That's what we call a jaspilite. So this is the problem, actually. An iron formation as a chemical precipitate has got lots of silica as well as iron oxide. And what you want to mine as a miner, if you are interested in mining iron ore, you want to mine the hematite or the magnetite, but not the silica. You want to find something that is much less silica and much more enriched in iron. Now nature does that for you through 2 processes. One, it can do supergene enrichment, in which the silica is leached out through weathering processes and leaving behind a porous and much more iron-enriched residual ore. And that happens in relation to a weathering zone, a zone of like an unconformity surface or something like that. The other process is hydrothermal, where you might have hydrothermal fluids coming from the interior, and they're leaching out silica as well, leaving behind a more iron-rich sort of product. So you get both processes, hydrothermal or due to weathering processes that can enrich a proto-ore which starts off as a banded silica and magnetite or hematite-rich iron formation to produce an ore that is much richer in hematite or magnetite, which can then be mined at a much higher iron grade. Now the process of how iron ore is actually formed can be found on a local scale when you have a swamp, and in a swamp you have a lot of organic activity producing a reduced sort of soil horizon with ferrous iron in a reduced form, and you have an aquifer that may have more oxygenated waters from a recharge area. They're moving down, and when these oxygenated waters may interact with this more reducing sort of soil horizon with reduced iron, it will actually oxidize the iron and produce hematite or something like that on the interface between the reduced soil and the aquifer. So this is what we call bog iron ore, and it was actually a big source of iron ore in the old days before people had access to the big iron mines. So this is a kind of a natural laboratory, a natural process which you can observe on a small scale and gives you some idea of how you can form perhaps a very big one. You need to find some place where you can take reduced iron and oxidize it, and that will produce a precipitate of iron oxide. So this kind of thing has led to the upwelling hypothesis for the formation of these platformal iron formations. And the main thing about iron is that when iron is as the ferrous iron, which is Fe2+, Fe2+ is soluble in water, and it readily dissolves in seawater, but it's under reducing conditions. When it gets oxidized to Fe3+, it is immobile and does not dissolve very easily in the water. So if you want to dissolve iron ore, it has to be in a reduced form rather than an oxidized form. And when it is oxidized, it then precipitates as iron oxide or iron hydroxide. So this is the thing. The iron solubility is controlled by the redox state. And so the conversion of Fe2+ to Fe3+ is achieved by oxidation. Now, it is postulated that the late Archean oceans were stratified oceans. The deeper parts of the ocean was anoxic. It had no oxygen. And it had no oxygen because, well, there was really no oxygen in the atmosphere either. The atmosphere was free of oxygen in the Archean and also in the early Paleoproterozoic. So therefore, the ocean was also mainly oxygen-free. Now, the source of iron that is dissolved in the oceans is through hydrothermal circulation at the mid-ocean ridges. This is where there is an interaction of hot magma with the ocean. And this hot hydrothermal solution can dissolve iron that is present in the basalts, alter them, removing iron and manganese, which go into solution as Fe2+, Mn2+, in this deep anoxic ocean. So there's always a source of this dissolved iron and manganese from this hydrothermal alteration process. So that is the ultimate source of the iron. The iron then gets dissolved in ocean water and is then present in this deep anoxic water. Now, what happens on the continental shelves, on the other hand, is something totally different going on there. because here in the shallow shelf, we have seen that this is where the carbonates are being deposited, and the carbonates, as we have seen, are full of stromatolites. So the stromatolites are undergoing photosynthesis, and the photosynthesis is releasing oxygen as a byproduct. So the waters in the very shallow regions near shore and in the subtidal zone are being pumped full of oxygen as a product of photosynthesis. So that water is weakly oxygenated because of this process. The origin of this oxygen is from photosynthesis. So only this very surface layer at the top has got oxygen. The atmosphere itself has got no oxygen. The deep ocean has got no oxygen, and it dissolves iron as Fe2+. Now we have waters upwelling into shallower regions like you see in this diagram. So the deep ocean waters with dissolved iron and manganese, they are upwelling to the shallow water where they can mix with the oxygenated water. That's when they on a large scale, these upwelling plumes will then precipitate iron oxide, which settles down as a chemical precipitate to form iron formations. And at the same time, you may also be dissolving or precipitating silica, and you get the alternation of iron and silica-rich layers to form banded iron formations. So, and there may also be a biological control, which is now being recognized as being very important. There are certain types of bacteria that are involved in the conversion of Fe2+ to Fe3+ in the photic zone, and they can help in this precipitation of iron oxides. So here's just another version of the same sort of story, upwelling of iron in a dissolved form, iron and silica going into the shallow water where they mix with oxygen and deposit iron formations full of iron and silica. So if you look at iron ore deposits, there's a whole list of iron ore deposits in South Africa, but by far the biggest one is the Sishen mine with more than 2.3 billion tons of proven reserves at a grades of greater than 60% iron ore, which is quite a nice grade. And then there are other deposits. The Tabazimbi one is the one that is currently being mined as well as the Sishen mine, but it's very much smaller than the Sishen. So if we look at Sishen here, this is the biggest iron ore deposit. And when you actually look at the iron deposit itself, which is a lot of which is hematite, you can see there is a lack of silica in the banding because the silica has been leached out, and that is what creates the high grade. And in this case, the leaching is because of the presence of a major unconformity surface just above the iron formation and was formed in the Paleoproterozoic. This is a Paleoproterozoic erosion surface, and during that formation of that unconformity, there was leaching of silica and upgrading of the remaining iron ore into high grades. And some of this material has even been reworked as a conglomerate with iron ore pebbles, with hematite pebbles overlying the massive hematite ore. And all of this is mined at the Sishen deposit. The Sishen is a large deposit extending over several kilometers and with several big open pits. This is looking north and looking south, and these are blast holes, and this is during the blasting. So it is the biggest, has a dedicated railway line that was built to export the iron ore directly from Sishen out to at Saldanha Bay north of Cape Town, and there's also other railway connections to export ore through the port at Port Elizabeth. So we have the export terminals for that. The other smaller deposit, the Tabazimbi iron ore mine, is about 100 million tons at 56% iron. It's not as spectacular in size or in grade as the Sishen mine. Okay, so we have talked about iron ore, and I think in Brazil you have much more impressive iron ore in Brazil, the biggest iron ore deposits in the world. So it's nothing new to Brazilian geologists. But the manganese deposits that we find in the upper iron ore is unique in the world and is the largest resource of manganese in the world. If you look at that resource, 81% of the world's reserves of manganese are found, and it's all mainly in that Kalahari manganese field in just one unit, one horizon that is about 20 meters thick and extends for something like 50 kilometers. So it's a very, very impressive amount of manganese ore in one sedimentary basin. Again, there's quite a lot of different deposits that are known and have been worked in the past. Some of them are primary, others are secondary weathering-related manganese deposits. So in South Africa, we have this, the manganese deposits constitute what is called the Kalahari manganese field. It's just south of the Kalahari Desert, and in the upper part of that Griqualand West subgroup in the Voorwaarters subgroup of the Postmasburg group. And here we see the manganese units. They are associated with iron formations, which are shown in the pale gray colors, and there are 3 manganese-bearing horizons, the lowermost one of which is the most important one, and this is the Hotazel formation, and this is the main manganese-bearing horizon. And there are 2 others as well, which are also being looked at from the point of view of ore reserves. So here is the geology of this Griqualand West region, where we see the geology is a bit more complicated because there is some thrusting over here associated with Proterozoic deformation, and associated with this horizon, this yellow horizon over here, this is the Proterozoic sediments which are overlying these later Archean to Paleoproterozoic carbonate platform, and it's on that boundary, on that erosion surface, that you find the major iron ore deposits at Sishen and Beershoek to the south here, which are developed within the lower iron formation. And then when you go stratigraphically higher up to the north, you find the upper iron formation exposed here, together with the manganese deposits. And this is what constitutes the Kalahari manganese field. And there's a whole series of deposits and mines extending over about 30 or 40 kilometers of strike length in this area. And there are 2 styles of manganese ore as well. There is what is called a low-grade proto-manganese ore, which has got a different mineralogy, and then there is what is called a high-grade or black rock type manganese mineralization, which is due to a later hydrothermal overprint, which has sort of changed the mineralogy of the manganese ores as well. But they're all sort of stratiform manganese deposits, all related to this some chemical precipitate in this Paleoproterozoic ocean. So this is one of the biggest mines over there, the Mamatuan open pit mine, which shows the manganese-bearing ores down here in black, overlain by a much younger sedimentary cover of Kalahari sands, late Cenozoic in age. And in the background, you can see one of the other manganese mines, which is an underground operation in the distance. This is the Chuaning mine, which has 200 million tons at about greater than 40% manganese. The manganese itself occurs as various manganese silicates and manganese oxides. So these are some of the main manganese-bearing minerals. Brownite, which is one of the primary low-grade ores, and Haussmannite and Bixbyite, which are found in the hydrothermally overprinted ores, the secondary sort of manganese ores. And there's also lots of other manganese oxides, in general, silomelane or WOD. And the Mamatuan mine here has got reserves of 400 million tons at greater than 35% manganese. And the ore body is about 19 meters thick with an overburden of these Kalahari sands. So it's almost like mining a coal seam. It's flat-lying and continuous for 40 kilometers. And they mine this face, and this mine, this is the biggest manganese mine in the world. They advance the face by 10 meters a year. And they've got another 30 kilometers to go. So it's a, this is the world's biggest manganese resource by far. They'll be mining here for the next few hundred years before the manganese runs out. It's incredible amount of manganese. And again, here we can see this massive brownite, haussmannite ore, silomelane, there's some, and then covered by the younger sedimentary cover. So how do we form the manganese? Well, in exactly the same way as you form the iron ore. Source of the manganese is hydrothermal circulation in mid-ocean ridges. Manganese is soluble in Antarctic deep waters, and as this manganese welds up to the near the surface in the shallow shelf regions, it mixes with oxygenated shallow waters, which are oxygenated due to photosynthesis from the algal mats, and by mixing with oxygenated waters, you simply precipitate manganese oxides, brownite, and even manganese carbonate is precipitated as a primary manganese carbonate, which is Kutna horite, a calcium manganese carbonate, and the manganese oxide called brownite. So those are the primary minerals, and then perhaps later upgrading events, hydrothermal events, could produce the Bixbyite, haussmannite bearing ores. We can actually see today an example of manganese formation in the Black Sea, because the deepest part of the Black Sea in Turkey, Iran, Russia, in that sort of region, the deepest part is actually very anoxic and euxinic, and there you can find manganese that is dissolved. And as you come to the very shallow water regions where it's mixing with oxidized surface waters, the manganese basically falls down to zero because it's precipitated as manganese oxides. So, and then the Kalahari manganese fields are also very famous for the whole host of secondary manganese minerals. It's got spectacular crystals of manganese carbonate, rhodochrosite, manganese silicates in its site, and a whole range of other very strange new minerals that have been found, like sturmanite and ettringite, and very complex sort of minerals due to the later hydrothermal activity and also due to weathering processes as well. Now, I have done with the mineralization of the iron and the manganese, but I just want to finish with the Transvaal supergroup by telling you about the Pretoria group and some of the mineral deposits there. Unlike the Chunispoort group, which has got the carbonates with gold and lead zinc mineralization and the iron and manganese formations, the Pretoria group, by contrast, has got very little mineralization. It's got just quartzites and shales. It's got a little bit of gold mineralization associated with veins, and some of the quartz has been recrystallized and used for glass making. But what is important here is that the upper part of the Transvaal supergroup, even though it's very poorly mineralized, is intruded by none other than the world's greatest ore. It's known as the Bushveld complex. So the Bushveld complex is intrusive into the Transvaal supergroup. It has transgressive relations with all these quartzites and shales, and it intrudes the Transvaal supergroup. And so we're going to talk in a future lecture tomorrow about the Bushveld complex and its mineralization, PGE, chrome, vanadium, and so on. But I have to tell you about another ore deposit that is found in the Transvaal supergroup, and that is in the metamorphic aureole surrounding the Bushveld complex. The Bushveld is so large, it stretches for 300 kilometers, and if you put the 300 kilometers of magma on top of a shale, it's going to get very hot. And that shale gets baked in the lower contact of the Bushveld, in these upper Transvaal Pretoria group shales, and they get completely baked and they form hornfelses with very large andalusite crystals. You can see here in my hand, these are big andalusite crystals, up to 2, 3, 4 centimeters in length, And this has formed the largest Andalusite deposit on Earth. It's being mined in several places. The Andalusite is mined as a source of refractory minerals. It's used for making bricks with a very high melting point. You know, it's used for lining steel furnaces because Andalusite has a melting point of about 1900 degrees centigrade. So we have this Andalusite deposit, and then the quartzites that are surrounding this, just close to the Bushveld complex, are very recrystallized, and they're used for glass making as well. So I will end with this photograph that shows an aerial photograph of the topmost quartzite in the Transvaal supergroup here, very recrystallized. The little shale horizons in there have been converted into a muscovite schist just through contact metamorphism, a muscovite hornfelds, if you like. And in this aerial photograph, if you go just immediately to the north of this quartzite, you have the Bushveld complex. So that's going to be what I will talk about tomorrow. In one of the lectures tomorrow, I will be talking about the Bushveld complex and its mineral deposits. Okay, so we'll stop here for the iron manganese in the Transvaal supergroup. So we will take questions.
Thank you, Sharad. And, e agora a gente pode passar a algumas perguntas, são 5 e 10. Se tiver alguma pergunta da audiência, por enquanto eu não estou vendo nenhuma pergunta vindo de colegas de fora. Tem o João.
A minha pergunta é sobre a presença de fósforo nos minérios de ferro e manganês. Se existe fósforo nos minérios de ferro e manganês.
Is there any phosphorus associated with the iron and manganese mineralization?
Not that I know of. There's very low phosphorus as far as I know.
Não que ele saiba, provavelmente muito pouco. Alguém mais? Francisco?
Eu queria saber o processo de deposição da sílica. Foi explicado o processo foi explicado o processo de deposição do ferro. Agora a questão da sílica, como é que a sílica é depositada? I'm asking about the process of deposition of silica, which is the process that alternates silica and iron in the banded iron formation.
I think there was a diagram that I showed which tries to show schematically this one here. So I think in this kind of a model, the silica is probably being precipitated more or less continuously, but when you have a big upwelling of iron-bearing deep waters onto the shelves, then there's a massive burst of iron precipitation that then produces a pulse of iron, which then forms a layer, but it's continuous silica on top of that. So when this pulse is finished, then there is just silica, then another upwelling of iron ore comes in. So these episodes of upwelling they're episodic, they're not continuous. And it happens today. If you look at off the west coast of Southern Africa, off the west coast of South America, there are these deep anoxic events. Sometimes they upwell onto the surface, and it happens every few years. it's not a continuous process, but it brings very sulfuric sort of deep water onto the surface. And in Namibia, I know near the town of Walvis Bay, you get these deep water upwellings, and you have sulfur, I think H2S, that is given off, which reacts with all the paint on the buildings and causes the buildings to go black in color. So every few years they have to repaint all the buildings because of these episodic upwellings. So the idea here is that the deep waters, which are anoxic, upwell onto the continental shelves periodically, and every time that happens, there's a mixing with the oxygenated waters, and iron formation comes out. But in the intervening periods, there's a continuous rain of silica that is precipitating, and that produces the banded nature. And in fact, silica and iron precipitate together to form jaspilite. Yeah.
Bom, muito possivelmente a precipitação da sílica é contínua durante toda a formação da camada, diferentemente da precipitação do ferro, que só ocorre em períodos de ressurgência. Quando as camadas mais profundas, que estão em condições anóxicas, são levadas à superfície, e o ferro 2, então, se oxida em ferro 3 e ao depósito dessas bandas ricas em ferro. Diferentemente da sílica, que se deposita continuamente, a deposição do ferro só aconteceria episodicamente porque está associado a esses eventos de ressurgência. Não teria a deposição do ferro se não fossem esses processos de ressurgência. Os processos de ressurgência são vistos hoje. Ele citou o caso aqui da África do Sul e da costa oeste da América do Sul, e um caso particular na Namíbia, que causa problemas até nas regiões costeiras, onde os prédios têm que ser continuamente pintados, né, por causa da influência dessa carga de sulfeto, de enxofre, que é trazida à superfície durante a ressurgência. Tempo para mais uma pergunta. A gente ainda não tem perguntas de colegas de fora. Mais alguém quer perguntar? Não? Então tá bom. Então, obrigado aí a todos. Amanhã voltamos a nos encontrar. Espero que nos encontremos mais com o pessoal que não está aqui também, via internet. Eu agradeço a presença de todos. Thank you very much, Professor Sharad. And I will meet again tomorrow morning at 9 o'clock. Okay? Thank you very much.